Hello, good evening, my dear lovely lions and warriors. Next chapter of Work Power Energy with all of you in the Roar series on our Vedantu JEE English channel. Hi, Soumya, Adiksha, Nikhil, Joseph. Welcome. I hope I'm audible to all of you and visible as well. Yep. So your Captain Shreyas sir is here on the channel, and we have completed quite a few chapters by now. Newton's laws, friction, vectors, 1D, 2D, relative, basic maths, so many things. So we are up to full speed, guys. Even 12th standard portion is in full swing. So if this continues, we will be reaching our goal. We will be completing as many topics as possible, by September, right? So guys, up to speed and full josh, full energy, hardly few months remaining. It's already September and just 4 months to go for our JEE mains examination. Let's gear up, guys. Let's go to the next gear. Let's, make sure that we are consistent. We are, up to the mark. We are not leaving anything. We are practicing enough problems at home. You're doing the DPPs. And if you're committed, guys, trust me, 99 plus percentile is yours. Okay. So let's gear up, guys. Your Captain Shreyas sir is here. Make sure you're liking the video and subscribing to the Vedantu JEE English channel so that you do not miss any of the classes. Yes, have you done the ritual? Have you smashed the like button? Chitra, hi Mohammed, hi Nikhil, good evening. Okay, and remember, there is also the scholarship exam which is going to go on in the couple of next weeks, and you need to register for it because there are a lot of exciting prizes to be won, scholarships to be won on different books and different courses. So make sure you are registered because obviously you will be taking up some or the other book or some service or some course from Vedantu. So if you are registered and you get the scholarship, you will get the maximum prize benefit, number one. Number two, prizes. Number three, you will get to know where you stand in the competition because people from different institutes will be taking this scholarship examination test. So let your friends know about it and make sure that they are competing against you in the MVSAT. The link for the MVSAT is there down in the description box below of this particular video, right? So as you go down right over here, you will be able to see this scholarship test. Just click on this particular link and you will be able to see all the details and you can enter your name, etc. and register for it. Okay. Chalo. Let's get started, guys. Yeah, by the way, it's available both in online and offline. Jan month end or Jan 15th, Soumya, nobody knows, but usually it is in Jan end second half. So anywhere after Jan 15th, it will be conducted. That's the usual ritual. Okay, let's start by work, then we'll slowly go on to kinetic energy, then potential energy, then mechanical energy, power. That's how the flow of the lecture is going to be. A lot of concepts in this chapter, and this chapter is also particularly important for even collisions, rotation, even SHM, even electrostatics, magnetism. You would have seen energy concepts come in most of the chapters. So you need to know how this works. Now, this Pandu pushing another Pandu. Obviously, this Pandu is doing work. So, the traditional notion of work, we think that, okay, I'm working so much, I'm hard worker. That is one thing. But in physics, work means when you need to define it in a particular way. You need a formula, you need to properly term it. So, we say that work is done when a force displaces a body or force displaces when it is applied, and the work which is done on a body can be positive, negative or zero depending on different things. So when I say that the work done is positive, that means I am doing work, I'm doing positive work. And if I say that I'm doing negative work, that means I am not doing work, somebody is doing work on me. And when I say no work is done, then I'm basically neither transferring energy from here to there. In a way, whenever in physics you say that you are doing work in general, that means you are transferring energy from one side to the other, from one body to the other, from one system to the other. So work is a process by which the energy gets transferred from one body to the other because that force ends up displacing it. Okay. So there is a work associated with it. All right, perfect. Even this person over here, you might have seen in when you are a kid, you might have taken a car and you might have pulled it back and then you leave it and the car goes forward, like the pull back action car. There is a spring in it. That spring ends up doing work on the wheels of the car, which pushes the car forward, right? So that is also an example of work. And so is this person lifting this particular weight, obviously doing work. She is applying a force and the weights are being lifted. The force is displacing that particular point where it is being applied. So 100% work is being done. The energy gets transferred from this person to these particular weights right over here. So I will say that work in general is nothing but transfer of energy by the application of force displacing it. We define our work to be the force along the displacement, multiplied by the displacement itself, multiplied by the displacement of the point itself. That is how you traditionally define work. You can see then, if there is some body and let's say this particular body moves over here, this particular body ends up moving over here. This is the displacement. Maybe there was a force acting on it. Like this. Okay. Maybe there was an angle between the force and the displacement. So then I can say the force along the displacement will be F cos theta, because that is that component. F sin theta is not along the displacement, so don't worry about it. So the force along the displacement would be F cos theta, and the displacement itself would be S. So that exactly would be the work, Fs cos theta or F cos theta into S. Because force is a vector, displacement is a vector, and I'm multiplying their magnitudes with the cosine of the angle between them, I use the definition of a dot product, which says that A dot B is AB cos theta. Magnitudes product into the cosine of the angle between them. Hence, I can put a dot over here, I can put S bar, and then I can put F bar right over here. You can see the outcome is a scalar quantity. So yes, work is definitely a scalar quantity. It is definitely a scalar quantity. You can also see the unit of work. Is a joule, and a joule of work is when a Newton force in the displacement, a 1 Newton force in the direction of displacement displaces it by a meter. So 1 joule is when 1 Newton displaces it by 1 meter. That is 1 joule of work. Is that right, everyone? Yeah. All right. Test series for 12th board student. Jay will let you know, bacha. Don't worry. Hi, Harborine. Welcome. Gauri, don't worry. You just joined in. This is the first slide which I'm writing, but some slides I gave some example. You can just check it out. Okay. Yeah. Cool. So let me just block all these off for all of you. So either ways, this is the same thing. There is another unit of work which you must definitely have heard about, and that is nothing but an erg. And erg is nothing but when a dyne of force displaces it by a centimeter. This is a CGS unit, this is SI unit. You should also know the conversion factor. 1 joule is nothing but 10 to the power 7 ergs. 1 joule is nothing but 10 to the power 7 ergs. Now once we have this definition, remember one thing. See, this body, maybe it moves over here, displaces over here like this. Okay, and we had our force in this direction, and this was the angle. I said that you take only the force along the displacement, F cos theta, and you multiply it by the displacement. You will get work. So we said work was F cos theta multiplied by the displacement. You can do one more thing. So we said we can also do it like a dot product. So I can write it as F bar dot S bar. And the last way of writing the work would be, instead of splitting the force, you keep the force as it is. But instead what you do, you take the component of the displacement along the force. So remember, displacement will also have two components. One along the force, one perpendicular to the force. So you take the component of the displacement along the force, that would be S cos basically theta. S multiplied by cos of theta. So you can also write it as S cos theta multiplied by the force. All these three are eventually going to give you the same value, but it is the way or the manner in which you calculate it depending on the ease of the solution of the problem. If it is given in vector form, I cap, j cap, k cap, then obviously using this method will be much easier. If you can easily figure out the force in the displacement's direction component, then I think you will use this. If I know how much I have displaced in the force direction, maybe that is easy to calculate, then I will use this. At the end of the day, the work calculation will come out to be the same. All these three methods are equivalent. They will give you the same answer. Is that clear, everyone? Yep. Let me know quickly. Okay. Awesome. Is it necessary to learn kinematics or laws of motion? It is definitely better. I mean, it will definitely be helpful, because or else you might face some difficulty while defining force and then, displacement and velocity and all these things. Yeah. But if you know the basics, very basics, then it is okay. Ashwin, the session may go to 2 to 3 hours. Aram se. Easily. Okay. So that was work. Now, okay, this and all is here. Second. This one is over here. Okay. Now, as long as, our force is constant, I can use this formula F dot S, but the moment force is not constant, I will have to slightly modify it. Remember here, F vector, S vector, they both are, not going to change. They are always same. So this formula you generally use when force is basically constant. If it is a variable force, it will slightly change, we'll come to it. But before we go to that, there is a very important thing, and that is, what is the meaning of positive work, negative work, and zero work? Just take this particular example. I just gave you some idea at the beginning. When I say I'm doing positive work, that means I'm doing a good deed. I am transferring energy to the system. If I say I did positive work in pushing Pandu, that means I gave my energy. I had eaten something. I had eaten a nice pizza in the afternoon. So that pizza generated some energy in my body. So when I pushed Pandu, so I have done work on him. I have given my pizza energy to him, and maybe that is why he has gained some speed. So that is positive work. Just like this person over here, you are throwing the ball up, the hand pushes the ball, is transferring the energy from the hand to the ball. So the hand does positive work on the ball. So I would say the work done would be positive if theta is acute, because cos of an acute angle is always a positive number. In the first quadrant, cosine value is positive. So that way I can say the product will be definitely a positive number. Weightage of the chapter, I mean, it's important everywhere, like I said. So no point you asking, are there 2 questions or 1? If I tell you, guys, there are 25 questions which are going to come. There are more than 25 chapters, almost 25 chapters in physics. So what kind of weightage will you ask? If a question comes which involves the concept of potential energy in magnetism, what will you say? Is it a question just purely from magnetism? No, right? You will need that concept of work energy. If you need to draw FBD, then obviously you need to know Newton's laws. If it involves velocity, acceleration, derivatives, you need to know basic maths and kinematics. So guys, stop categorizing, topics, weightage. These are all gimmicks which people will fool you, and if you fall for it, you will lose marks. Trust me. Yeah. Yes. Okay. So positive work means that external force favors the motion. You are keeping an acute angle. So theta is less than 90. So cosine will be positive. Can you tell me and think, what is the meaning of then negative work? It will be exactly opposite of this. If positive work means the external force is favoring it, it is transferring the energy, it is doing a good deed and helping that. Negative work means I am sucking that energy. I am taking away the energy from the body. I am not favoring the motion. I am against the motion of the body. So the force will act at an obtuse angle, because then theta, when it is obtuse, cosine in the second quadrant is negative. Cosine in the second quadrant is negative. So the value of the work will come out to be negative. So like this particular diagram over here, you can see the force is making an obtuse angle. So anywhere after 90 degrees till 180 degrees, the work done will be negative. There could be many examples of this. If you have watched the Spider-Man movie where the Spider-Man uses his webs to stop a train, he's stuck onto the back of the train, he's using his webs, and he's trying to stop a train which has lost control. The displacement of the train is this way, the force which he applies is in the opposite way. Spider-Man does negative work on the train because he is sucking away the energy of the train and helping to stop the train. So his force does not favor the motion, it's against the motion. So Spider-Man does negative work on the train which has lost control. Is that making sense? Yep. Very good. Similarly, my dear students, imagine the ball which you have thrown up. Imagine you are trying to catch the ball. Okay. So when you are catching the ball, what are you doing? You are absorbing the energy. You are taking away the energy. The ball had potential energy and then kinetic energy, and it is coming with a good speed. You are absorbing it by slowing it down. You are basically applying the force this way and you are slowly catching it. The force retards it. It's against the displacement and hence negative work is done. I hope this is clear. Similarly, okay, if this much is clear, guys, what would be then zero work? Zero work is when either you don't apply force only, or you don't have displacement, or in terms of angle, the work done will be zero if cos is basically zero. That means theta is 90 degree. That means theta is basically 90 degree because cos of 90 is zero. Whenever the force is perpendicular to the displacement, you will see the work done will be zero. There are many examples of that. Imagine I take a ball, attach it to a string and I whirl it around like this. The string is pulling the ball always towards the center and the ball is moving along the circle. So the ball's circular displacement versus the tension force is always going to be perpendicular. So the tension never does work on the ball which is attached to the string as it goes around. In fact, think about it. How can tension do work on that moving ball? Because if it is perpendicular, it can never ever change the speed. It will only change the direction. It cannot give energy nor can it take energy. It maintains the speed. So it is not sucking the energy nor is it giving it. So it does zero work. So it ends up doing zero work. Even anything which goes around the earth like a satellite, or even the earth going around the sun, for example, almost circular orbit. Let's take it circular. I know it is elliptical, but for the time being, let's take circular orbit. So in the circular orbit, the gravitational force will be always perpendicular to the displacement. That gravitational pull on the satellite towards the earth never can add or take away the energy. It continuously rotates with a constant speed, hence does zero work. Now, Lot of people have this confusion about zero work, where you might have heard about this example. Imagine there is a person and he's trying to push a box or a wall, but that particular box or that wall doesn't move. That particular box or wall doesn't move. It is basically at rest. He's pushing it. So is this Pandu doing work or not? If it is at rest, that means displacement is zero. Then what do you think about the work? Is Pandu doing work on the box? Yes, Manika, I do remember we enthused the long old picture. Definitely. It is, Luna, you can start your preparation now. Also, you can try, you can get 95, maybe second attempt you will get 99. But if you don't try, this attempt you will definitely not get 95, and next attempt you will struggle, and maybe you will think of either a normal private college or taking a drop, which I don't want you to do. I think whatever days you have, you utilize them. Well, the answer for this question is 0. But then, why is this guy going to be tired? How come this guy is tired? Right? You might think about it. The answer to that is, see, that Pandu, that person, never did work on the box, correct? Because he never gave the energy to the box. In fact, the energy was consumed within himself in muscular form. Increased metabolic activity. His heart rate might have gone up. He might have felt tired because he is putting pressure on himself. So it is lost within himself. He starts sweating, metabolism increases, heart rate might have increased. So he is not doing work on the box, rather within himself, and that's why the energy just gets lost into the surroundings. Maybe his body might become a little bit hot. Got it? Yep. I hope this is absolutely clear. Everybody, absolutely clear. Great. Now, this is why I said either force is 0 or displacement is 0 or theta is 90. There is no displacement, perfect. No work. If there is no force, then what work? No force only. Why will there be any work? Force is there, displacement is there, but perpendicular, then also no work. Now, I can think of another beautiful example. I'll come to it. So this is like the summary point. Theta is acute, work is positive. Theta is perpendicular. Oops, I think it should have been 0. I don't know why they put something else. My bad. Work done over here is big fat 0. Yep. Theta is obtuse, work done is negative. Perfect. I remember one beautiful example, and let's see whether you guys can solve this particular question. Imagine there is a person and he's just taking a walk. He's moving like this. Question is, friction will act on the legs of the Pandu. Obviously, when you're walking, you take help of friction, right? So, question is, what will be the sign of the work done by the friction? What will be the sign of the work done by the friction? Okay? Will it be positive, will it be negative, or will it be 0? Now, usually what people think is that, okay, the person is moving in the front, friction, bad guy, so friction will act behind. So, friction is against the displacement, so work done will be negative. That's what usually people end up thinking. Yep. That's what usually people end up thinking. But let me tell you, that is not the correct answer. If you mark that, you will not get, no, you will not get marks, you will get negative marks in fact. You will get -1 in the JEE mains examination. See, when the person's foot, imagine this is the person's foot. I'm just showing some weird drawing, but just imagine this. When the person's foot touches the ground, that foot never practically moves. That foot never practically moves unless it is lifted again and the next foot is in contact. So, meanwhile, that other foot might be in air, other foot which is there. Wow, this leg is not that great. Okay, this other foot is in air, and you will see this particular leg will finally bend like this, and you will take this leg and finally put it here. Till that time, this leg has not moved. Really, you should See this, that this particular leg is at rest. The friction acting over here, the friction acting over here, the friction which is acting over here is actually static in nature. The friction acting over here is actually static in nature because there is no relative sliding between your foot. You don't drag your feet and move like a kid. You keep your foot at rest unless the next foot comes, and then the next foot is at rest and the other foot is in air, and then it falls onto the ground, that is at rest, and then this foot lifts off. So your feet never actually slide on the ground. So there is static friction. So guys, there is no work done by friction. So actually speaking, the work done by that friction is zero. You might be moving, but friction is not moving. This is an amazing, amazing, amazing phenomena, amazing concept. You can think like this, that why will friction even give energy or take energy? In fact, it is the person's own metabolism, muscular energy, which is making him move forward. The ground was just helping him like a support, but his actions of walking or running or moving his legs, that was consumed from within. It was not given by the ground, by the friction. Okay, so it was his own muscular energy which was consumed in making him walk. Okay, right. I am pretty sure everybody will remember, Manika. Long time it is, but definitely I'll ask. Okay, free mock test source Luna. Right now you can know, as of now you don't have, but if something comes up, I'll definitely let you know. There was something in the plan, like few mock tests we wanted to give you free. I'll definitely let you know. Okay, so stay tuned on the channel, stay subscribed. If that comes up, I'll definitely let you know. Cool. Now tell me, can normal force, can normal tension, pseudo, etc. do work of all kinds, positive, negative, zero, etc. Pseudo force, static friction, kinetic friction. What do you think? Do you think they can do positive, negative and zero work? Yep. So very, very interesting question. Lot of you might be thinking that certain forces will not do work, like for example, normal. So if I have a box, and this is a surface, and if this moves like this is the displacement, the normal force will be here. Obviously, in this case, the work done by the normal force is definitely zero. No doubt. Because the angle between the force and the displacement is 90 degree. So cos 90 is zero. No issues. But imagine a scenario where this is my hand, okay, this is my hand, and I am lifting this box. I am basically lifting this box. If I lift this particular box, that is the direction of the displacement. Obviously, in that case, the normal force will be like this. Oh, it's in the same direction. So in this case, the work done by the normal is definitely positive. Work done by the normal is definitely positive. What if, imagine you are trying to stop some object. It is trying to move over here. That is the direction of the displacement. You are using your hand. To stop it. So in that case, the hand will apply a normal force in this particular direction. So you are trying to stop. Normal force is trying to retard it, trying to decelerate it. So in such a case, you can see that the work done by that normal will be obviously negative. So yes, normal force can do positive work, negative work and zero work. All of them are possible. Not just this, even tension also, we can say the same thing. So imagine I am taking a ball, connected it to a string, attached it to a point over here, and the ball goes in a circular path. So in such a case, the displacement is along the circular path. The tension force is obviously perpendicular, and the work done by the tension force is obviously going to be zero because it is perpendicular. Imagine you have a dog. Imagine you have a dog. This is our amazing pet dog. And you are pulling that dog. You are pulling that dog by a thread. So in such a case, obviously there is tension in that thread. There is tension in that thread. And that dog does not want to come out, whatever, for some reason, but it is ending up displacing. Obviously, in such a case, tension and displacements are making acute angle. So work done by tension will definitely be positive in nature. Work done by tension will definitely be positive in nature. Imagine you are trying to lower a bucket. You are trying to lower a bucket of water, okay, slowly by holding this thread. You are lowering it, so the displacement is here. So you are lowering a bucket of water. In such a case, where is the tension force on that bucket? It is right over here. Displacement is exactly opposite. So obviously the work done by the tension will be negative in nature. Work done by tension will be negative in nature. Amazing. Similarly, you can also comment for other forces like pseudo force, etc. So imagine you are in a frame of reference of a lift, and this particular lift is accelerating upwards. So that lift is a non-inertial frame. That lift is a non-inertial frame. So if you have some body which is going down, some body which is probably going up, some body which is either at rest or maybe somebody which is just going like this, displacement. This is the displacement, this is the displacement. So in this case, the pseudo force, in this case, the pseudo force on this body will be downwards because acceleration is upwards. So pseudo force will be here. Here also the pseudo force will be here. Here also the pseudo force is here. Here also the pseudo force is downwards because pseudo force always acts opposite to the acceleration of that lift or that frame which is accelerated. So in this case, obviously you can see that the work done is positive. You can see here the work done is negative, and obviously in both these cases the work done is zero because it is at rest or it is perpendicular. Is that right, everyone? Yep. Sir, when is the portion completed? Ashwin, we'll try to maximize the completion by October. I mean, yeah, by October you can think that, yeah, almost done types. Cool. Okay, okay. Now, what about static and kinetic friction, guys? What about static and kinetic friction? Do you think they will also end up doing work? Positive, negative, etc. The answer for that is yes. Definitely it can do positive, negative, or even zero work. Imagine you are trying to push a box, but it is not moving. Because it is not moving, displacement is zero. Static friction will act against it, and 100% in such a case, the work done by the friction will be zero. Work done by the static friction will be zero because it was at rest. But imagine a scenario where there is a box, it is moving like this, maybe because it was on a conveyor belt. Maybe it was on a conveyor belt. This is like a belt. This belt is pulling it, is being pulled by this conveyor belt. In such a case, maybe the friction on that box will act like this. Friction on the box will act like this. It is being pulled here. So obviously the work done on the box will be positive. The work done on the box will definitely be positive. At the same time, if the friction acts rightwards on the box, then it will act leftwards on the belt. This will be reaction. This will be reaction of Newton's third law, and then this would be the action of the Newton's third law. If the belt applies a force this way, the box applies a force this way on the belt. Opposite, equal, but different bodies. They won't cancel each other. So hence, I can clearly say that the work done on the belt will be now negative because this force is opposite to the displacement. This force is opposite to the displacement. Is this clear? So glad, Luna. Thank you so much for all the belief. Sir, bob of a simple pendulum also zero work. Yes, Soumya, definitely, because the bob of a pendulum moves in a circular arc. Tension always acts perpendicular to the displacement. So never will it do work. In general, centripetal force never does work on a circular path. Yeah, it will not do work. Same thing you can comment about kinetic friction also, guys. So even kinetic friction can do all kinds of work. So if you are wondering, does pseudo force do work? Yes, pseudo work does exist, and all forces can do all kinds of work. That is what we see over here. Now, before we go ahead, let's take up more questions, guys, coming up on your screen. Starting off with a very basic question. Let's see if you guys can do it. If the force acting on a body is given by 2I cap minus J cap plus 3K cap Newton, and the displacement, sorry, this is force number 1. The next force on the body is I cap plus 3J cap minus 2K cap Newton, and the displacement is found out to be 2I cap plus J cap minus K cap meters. Question is, what is the work done? What is the work done in such a scenario? Let's try to solve this question, my dear students. There are two forces acting on the body and the displacement is also given, and we have to find the work done. In order to find the work done, we have to do the dot product of force with displacement. Why did I choose dot product? Because it is in vector form. Okay, but which force will I take? Well, there are two forces. Both the forces acting together will produce a net force. So first things first, let's find out the net resultant force. The net resultant force will be the sum of these two, 2I cap plus I cap, 2I cap plus I cap, plus minus J cap plus 3J cap, and plus 3K cap minus 2K cap. That is what our resultant should look like. So 2I plus I is basically 3I. This will be nothing but plus 2J cap. This will be nothing but plus K cap Newton. So that is your net force. You have to take the dot product with the displacement to get the total work. So work will be the force dot displacement. So 3I plus 2J plus K dot producted with this thing, 2I plus J minus K cap. So what do I get? 3I into 2I, 3 2s are 6. 2J into J, 2 into 1, 2. Plus 1 into minus 1, minus 1. So 6 plus 2, 8. 8 minus 1 is 7. So 7 joules is the answer. 7 joules is the answer. Yep. Correct, Soumya. You added both the forces and then finding the resultant. Then you take the dot product with the displacement. Perfect. Everyone, Harborine, just check it out. 7 joules. Cool. Clear. Okay, so 3I cap plus 2J cap plus K cap was the force. Take the dot product with the displacement, 2I plus J minus K. So 3 2s are 6, 2 1s are 2, and 1 into 1 with the negative sign is minus 1. That's it. So 7 joules. Bharadwaj, little bit late, but I'm pretty sure you will be able to catch up. Join in. Yep. Bookish Tales, usually my classes are on Tuesdays in the evening, but things can change here and there. Just keep subscribed on the channel and be a part of the Telegram channel as well. Yeah, if you are not yet a part of our Telegram channel, be a part of it. It's right over here in the description box here. You can see, where is it? Telegram. Yeah, so that you'll get all the updates, number one. And any session that you miss, you can see it over here, Jungle Book. Okay. So when you go to the Jungle Book, you will see, you will have to enter your phone number or email ID if you are not yet registered, free account. You will be able to get all the old sessions, their PDFs, their links, their DPPs for all the subjects, everything in a very systematic manner. So no need of searching for any playlists. Okay. The next lesson will be circular motion. Next question coming up on your screen. Now imagine there is a lift of sorts like this, and there is this inclined plane, and there is this angle over here, and there is this box which is kept of certain mass m, and this is going up with some speed, and it ends up going and it ends up going with a velocity v for time t, constant velocity for a time t. This box is at rest on that rough incline. M is basically at rest on the rough incline. What is the question? The question is find the work done by normal, work done by friction, work done by gravity, and the net work in this particular case in some time t. So this entire system is going up, inclined plane block, the lift, everything with a constant speed. Find the work done by the normal, friction, and the gravitational pull. All the three forces, and then add them up to find the total work. Let's do this. Okay. Cool. Bharadwaj, like I said, by October. Okay. Yeah. So let's start with the question, guys. First of all, let me get rid of this. Not needed as of now. Let me start by drawing the free body diagram of this particular mass. So what are the different forces acting on it? The different forces on it will be, one is obviously mg. Mg will be here. Mg will be downwards. Normal force will be obviously like this. And friction, because the box will try to slide down, hence the frictional force will act in this direction. Now, if you notice, mg technically has two components. Mg technically has two components. One component is right over here, which will be mg cos theta, because this angle will be theta, and this component down here would be mg sin theta. Because this box is at rest, clearly mentioned that it is at rest, therefore all the forces should balance each other. All the forces should balance each other out. So therefore, I can say that the normal force will be balanced by mg's cos theta component, and the frictional force will be balanced by the mg sin theta. Okay. So normal force I know, frictional force I know. Why do I need it? Because to find the work, I need the force. Without the force, how will you find the work? So the first step was to find the force, and then I think we can go with the problem. Okay, great. So now I know all the forces values. And what about the displacement? Well, it moves with a speed of v for a time t. So that means if it is moving with a constant speed, and it moves like this, the displacement will be the velocity multiplied by the time. Hence the displacement will be v into t. So it moves an amount of vt. Oh, so we have got most of the things now. Let's start showing them up. So this is our displacement right over here, which is vt. But I can see some of the forces are not along the direction of the displacement. They are making certain angles. What angles are they probably making? Let's find them out very easily. So think about it, guys. If I just draw this dotted line right over here and extend this right over here, you can see if this angle is theta, this is also going to be theta. So therefore, this angle is definitely theta. If that is theta, this is 90 minus theta, and then this would be theta. This is 90 minus theta. Again, this is theta. This is 90 minus theta, and again, this is theta. Remember the division of 8 trick which I have told you in Newton's laws. If you have to find the angles, divide it into 8 parts: vertical, horizontal, incline, and perpendicular. You will get 8 parts. If you know any one angle, leave one part, go to the next, that will be the same angle. Leave one part, go to the next, same angle. So this way you can easily find the angles in such inclined plane problems. I hope this is clear. Kavita, I have shown you where to find constraint motion. It's there in one of the older classes. Just search for constraint motion multiple pulleys on this channel. You will get it. It's a beautiful video explaining all the kinds of constraints. All right. Now, in order to find the work done by gravity, force of gravity is mg, displacement is vt, the angle between the displacement and mg is 180 degrees. So hence, I should put cos of 180 degrees. So cos 180 is -1. So minus mgvt is the answer for the work done by gravity. Did you see that displacement is up, mg is down, so it will be doing a negative work. Similarly, try to find the work done by the normal force. Well, normal is here, so force is n, displacement is vt, cos of basically theta, but wait a minute, I know what is normal, it is mg cos theta. So normal was mg cos theta into vt into cos theta. So I can just say it is mgvt cos square theta. That is the work done by the normal. Let's go for the work done by the friction. Work done by the friction, guys. Everyone with me on this? Work done by the friction. Can you see this particular angle over here? This particular angle over here is actually 90 minus theta. That's the angle between friction and the displacement. So be careful while solving it. So the frictional force into the displacement into cos of 90 minus theta. Frictional force, we just figured it out to be mg sine. So it was mg sine theta into vt. Cos 90 minus theta is basically sine theta. So hence it will be mg vt sine square theta. That is the work done by the friction. So we have found all the three different work by normal, friction and the gravitational force. Perfect. But that's not the end story. The end story is to find the total work done. So when I try to find the total work done, do you see mgvt is common. mgvt is common everywhere. The first term has -1. The next term has cos square and sine square. Cos square theta and sine square theta. But don't we know the trigonometric identity? Sine square plus cos square. What is it? It is nothing but 1. So yes, so this is -1 plus 1, which is a big fat 0. So the total work done was 0. All the forces were working, but as a whole, the net work was 0. Beautiful question. Sagar, definitely you can watch it for revision. Sunita, 2-3 hours class. We Enthuse Club, yes, thank God you have risen from the grave after a long time. I'm so glad. Thank you so much for posting that reel. Yep. Okay. So in this question, what we did is, in order to find the work, we first found out the forces. Without the force and the displacement, we can't proceed. So I have drawn the FBD, normal balanced mg cos, friction balanced mg sine. Displacement was Vt. For work done by gravity, gravitational force multiplied by displacement, but the angle was 180, which makes it -1. For normal force multiplied by the displacement into cos of theta. So that's why it became mgvt cos square theta. Cos into cos became cos square. Friction was here, made an angle of 90 minus theta with the displacement, but cos 90 minus theta is sine. This sine and this sine became sine square. If you add this and this, mgvt is common. -1 from here, cos square from here, and sine square from here. Sine square plus cos square is 1. So 1 minus 1 is 0. That's why the answer for the total work came out to be 0. Is that okay, Luna? Right. So beautiful questions, guys, these are. And you can see that how our knowledge of just a simple concept of work is improving. We have seen different works done by different things, as well as this complex question. Okay. Let's see one more question, guys, coming up on your screen. Let's see one more question, guys. Okay. Let's see one more question. Imagine there is a block of, say, 5 kg and it is being pulled by a rope. There is a rope which is being pulled like this, and let's say the acceleration of this particular block upwards is 2 meters per second square. So if it starts from rest, find work done by tension, work done by gravity, the total work done in 2 seconds, in the first 2 seconds. That is the question. Find the work done by tension, gravity, and the total work in the first 2 seconds. Okay. I mean, let's first understand, because it is accelerating 100%, there is some tension which is acting on it upwards. There is also mg, which is 5g acting downwards. As a result, it is accelerating. So obviously this will do work, and in 2 seconds it will move some amount. Can we find that amount? I think so. If you just think, if it starts from rest, it accelerates, it covers some displacement, and in t is equal to 2 seconds it has some displacement. That would be given by ut plus half at square. So initial speed 0, acceleration is 2, time is also 2. So in this case, 2 cancels, I'll get the displacement as 4 meters. I'll just get the displacement as 4 meters. Perfect. Now I'll find what is the tension force, because tension is not 5g. A lot of people will say tension is 5g. That's a common silly mistake in this type of questions. In fact, look at it carefully. Tension minus 5g is mass into acceleration. Mass into acceleration. The net force is mass into acceleration. It is not equal. That is the reason why it was accelerating in the first place. So tension will be 10 plus, minus becomes plus, 5g means 50. So tension will become basically 60 Newton. So starting off with the work calculations now. Work done by tension. Tension is upwards into displacement into cos of 0. Why cos of 0? Because the displacement is also in the same direction. We just figured it out. Displacement 4 meters would be in the same direction. So tension force 60, displacement 4, cos 0, 1, 6 4s are 24, so 240 joules. That's the work done by the tension. Similarly, work done by gravity. Gravitational force 5g, displacement 4, or the displacement I'll put it here, into cos of 180. Why 180? Because force and displacements are opposite. So this will be 50 into 4 into -1. So the answer will be minus 200 joules. Lastly, the total work done will be 240 minus 200, hence it will be 40 joules of work. That's the answer. Is that clear? Yep. Perfect. First, let me complete magnetism. After that, we'll be having EMI AC. Okay? We'll be having EMI AC. All right. Great. Hello, Rani. Hello, everyone. Come on, let's go ahead. Now, let's go to the next concept where the force is not constant, rather variable. If you see all these questions, the forces were constants. They were, not changing with time. So now let's see the situation where the work done is to be calculated because of a changing force. So what we do is, imagine the body moves a small displacement ds. In this process, our force will hardly change. So for that small displacement, the work for a small displacement will be dw, and this dw will be a dot product of that particular force and that particular displacement ds. So now if I want to find the total work done, maybe I was going like this and maybe like this. This was the initial point. This was our final location. The total work done from the initial position to the final position along that path will obviously be the sum of all the small work done for all the small displacement. So sum of all the work is nothing but integration of dw. Integration is nothing but a symbol which is a replacement of summation of small, infinitely small things, okay, from one point to the final destination. So integration of dw means you have to integrate to find the work. Therefore, it is integration of nothing but the force, with respect to our displacement, So this becomes our formula, guys. this becomes our formula for variable forces. Now, it might so happen that our force might be given in vector form and so is the displacement, and you might have to integrate it with the limits initial to final. So if the force is given, for example, as fx I cap plus fy j cap plus fz k cap, for example, and the displacement, small displacement will be dx I cap plus dy j cap plus dz k cap. If you take the dot product of these two, what will you get, my dear students? I cap will multiply by I cap, so you will get fx dx integration plus fy and dy integration, fz and dz, so integration of fz and basically dz. So if it is given in I cap j cap form, then you can use this simple formula to find the work done. Here you are calculating only the work in x, here you are by y, here you are doing it by the z component of the force. Why is ds this? Because think of it like this, that any small displacement which you have will be made up of, components, right? Some x component will be there, some y component will be there, some z component will be there. So that is the reason why I have written displacement as dx I cap, some y cap and something j cap. But these are very, very small, teeny weeny displacements. And when I take the dot product, I cap into I cap is 1, only x will multiply with x, y with y and z with z. Is that absolutely clear? Give me a thumbs up. Hi Tanuja. Yes, and in ideas we are trying to complete as much as possible by September and October. That's it. Is that okay? Yes, Pandu comes once in a while. Pandu is our special character, not every time, right? Alekia, yes, I do remember. Oh my God, you already went into AIMS? Wow, I think yes, the counseling is going on. That is so cool. 675, 720, you are a AIMS student. So proud of you. Very good, very good. Really, really happy when you go into IITs, AIMS, AFMC, JIPMER. These are like the colleges that you should be proud of, you should brag about. And I feel extremely happy when many of you come over here, and not just you guys, Alekia, so many of you, after going to any college, you come back to the channel and tell, sir, do you remember me? I was your student. I attended these classes and now I'm in this college. I feel extremely happy. Thank you so much. Okay. Whenever you have integration, you should also think about one more thing, and that is none other than area under the curve. So obviously, if you draw force versus displacement graph, and let's say that particular graph happens to be something like this, then the area under the graph, the area under that particular graph gives you the work done. The area under that graph basically gives you the work done. So the area under the force versus the displacement graph, area under the force versus our displacement graph gives you the work done. Gives the work done. Cool. This is what I have written down here and probably even here. Okay, perfect. So maybe we can also solve some questions on this. Let's solve some questions, guys. If our force is 3x minus or 3x square minus 2 Newton, find the work done to take the object from 1 meter to 2 meters along x-axis. Along x-axis. That is the question. So this is our x-axis, let's say. This is our x-axis. The body was initially over here, finally over here. So you have moved like this, but the problem is the force is not constant in this particular region. It is variable. So I will have to use integration. There is no other option or choice that I have. So let's start with it. Work done will be integration of force dot displacement. But the good part is here the force is along x and the displacement is also along x. So I can replace it with the x component of the force into dx. Simply put, fx dx. I don't need any cos, sine, anything. Only the force is along x and displacement is along x. So ds becomes dx. F is the F force along that x direction. So that force is nothing but 3x square minus 2 dx. Limits will be initial to the final location. So initial will be the lower limit and the upper limit will be the final location's coordinate. That's all. Good evening, Srinivasa Rao. Okay, very good. So just integrate this, guys. So 3 into integration of x square. Actually 3x square's integration. Actually 3x square's integration, do it separately, minus 2 integration of dx. And limits are 1, 2, 1, 2. 3x square integration. X square's integration is x cube by 3. 3 cancels. So it will be x cube. And here you will have 1 and 2. Minus 2. Integration of dx is just x. 2 and 1 over here. So put 2 first. Then put 1. Minus 2. And then put 2. And then put 1. Perfect. So the work done will be 2 cube is 8. Minus 1. Minus 2. 2 minus 1 is 1. Perfect. 8 minus 1 is 7. So 7 minus 2, guys. So that is going to make it 5 joule. So the work done is basically 5 joules. Work done is basically 5 joules. Is that clear? Just check it out. Yes, Harburain. Yep. Somya, I think you made a small mistake. Yes, Ashwin, the answer is 5. Just see if you have made a small calculation error somewhere. All right. Great. Great. Moving ahead to the next question, guys. Moving ahead to the next question coming up on your screen. Now, in this particular question, the force is in 2 dimension. F is x I cap plus y j cap. Force is basically x I cap plus y j cap. And you have to move it from its initial location. We can take any value, guys. Okay, we can take maybe 1 comma minus 2 to the final location. To the final location, we can take some other value. Maybe, for example, this is 2 and this is 1 meter. Question is to find the work which has to be will be done. Okay, let's try to solve this question. This is a 2-dimensional question because I can see I cap and j cap involved. So I know when there is I cap, j cap, 2 dimensions involved, I can calculate x and y separately. So I have that liberty. So instead of writing f dot ds, I can think of it as if it is x I cap plus y j cap dot the small displacement will be dx I cap plus dy j cap. When you do the dot product, what you will be left is x into dx will be x dx, y into dy will be y dy. But you can separate out these integrals. Like this, x dx plus y dy. Why do you want to solve it together? The limits of x will be from here, starting with 1 going to 2. The y limits will be starting from minus 2 going to 1. Minus 2 to 1 and 1 to 2 for x coordinate. So x's integration is x square by 2, limits from 1 to 2, plus y's integration is y square by 2, limits are basically, from minus 2 to basically 1. Okay, put 2 here first, so 2 square by 2, then put 1 here, so minus 1 square by 2, plus first put 1 over here, so 1 square by 2, minus, then put minus 2 over here, minus 2 square by 2. Perfect. So what do I get? Here this will be 2, this will be nothing but 0.5 plus 1 square is 1, 1 by 2 is again 0.5, and this minus 2 square is like 2 square, which is 4. 4 by 2 is nothing but 2 again over here. Wow, interesting thing, guys. Something interesting is very happening. 3 missed. What is 3? Okay, 3 not here, maybe in the previous question. Okay, fine, we'll just come back. Okay, so minus 5, minus 0.5 and plus 0.5 cancel, 2 and minus 2 cancel, so the answer just comes out to be as 0 joules. Very interesting. Answer comes out to be 0 joules. Okay, so moving to the previous one. Oh, I missed that 3, is it, over here? Sorry guys, this 3 was missed. Sorry, my bad. So this 3 was missed. Okay. Sorry guys. So this will be nothing but 3 into 2 cube is 8 minus 1 minus, is that? No guys, this was fine only. What did I just do? X square's integration is x cube by 3. 3 got cancelled. It was fine only. Nothing wrong. Soumya? Sorry, Mercy. It's fine only. Okay. Let me put it over here. Integration of 3x square dx is basically 3 into x square dx, which is 3 into x square's integration is x cube by 3. So it is basically x cube only. Okay, fine. Okay, thank God. Even I thought, okay, fine, something is wrong. Okay, but it is fine. So anyways, this question's answer was 0 joules. Beautiful question. But now let's take it a step further and let's solve another awesome super duper question. Force is y I cap plus x j cap. This is crazy, guys. This is crazy. Okay, and you have to take the particle like this. This is x, this is origin, this is y. You have to take the particle like this. Along this path, question is find the work along the path shown. Find the work along the path shown. This is such a beautiful question. You will see why. Because number 1, it's 2D. Number 2, look at the I cap, it has y coordinate. Look at the j cap, it has x coordinate. So it is going to be very tricky. Okay? Yes. Yes, we are doing all kinds of questions, as many possibilities, models of questions. So that's why it's becoming a beautiful, beautiful question. Anyways, so let's start by dissecting the problem. I will divide the problem into 2 parts, one from here to here and one from here to here. If you just consider this particular part, okay, if you just consider this particular part, let's say I label this point as A, from O to point labeled A over here. Then along this path, the thing is, everywhere the y coordinate will be 0. The y coordinate will be 0. So if you see what the force might be, the force will be along this path 0. Y coordinate is 0, so 0 I cap. Yes, the x coordinate is different at different places, so only x j cap will be there. Therefore, the force between O to A, the force between O to A is just going to have x j cap. X j cap, interesting. This is not a force along x axis. It depends on the x coordinate, but that force changes with the x coordinate. As the x coordinate changes, the force also changes. It is increasing, you can see. And this force is definitely perpendicular to the displacement. Hence, the work done from O to A is 0 joules because it is perpendicular. Can you see that? The force is perpendicular to the displacement. Very interesting. I have dissected the problem into two parts. I have not yet solved the second part, but in the first part, the force just came out to be perpendicular. Wow, this is amazing. Now, imagine, we are doing concepts initially and then problems. I think you have joined in late, Agastya. So first we started with the concept, then problem, concept, problem. That's how the lecture moves. Now let's go from A to point P. Let's go from this particular point A to point P. Okay, let's see what happens from A to point P. In this situation, everywhere the x coordinate will be 3. X coordinate will be 3, but the y coordinate changes from 0 to basically 4. That is what is happening in this particular scenario. Okay, so what can you say about the force from point A to P? X coordinate is 3, y coordinate is changing, so I'll just put y in general, y I cap, but the x coordinate is constant, so which is nothing but 3j cap, 3j cap. Now tell me one thing, when you're going along this direction, which force component will matter? Will the y component matter or will the x component force matter? Obviously, this y I cap is perpendicular, it won't do any work, but this 3j cap will definitely do work from A to P. So I will say this y I cap doesn't do work. Why it doesn't do work? Because it is perpendicular, but this does work in the direction of the displacement. You can very easily see that. So therefore, the work done from point A to P will be only dependent on this 3 Newton force, displacing it by how many meters? 4 meters. So 3 Newton displacing it by 4 meters. So hence it will be 12 joules. Hence it will be 12 joules. Is that clear? Very good. So now we have found our final answer. The work done from O to point P will be work done from O to A plus work done from A to P. Work done from O to A was 0, from A to P was 12, hence the answer would be 12 joules. Such a nice conceptual question. This is a proper JEE advanced type of question. You don't have to do by resultant or anything else. Go step by step, part by part, divide the path into 2 parts or multiple parts and then solve the question. Understood, guys? Clear? Can we go ahead? Very good. Awesome. Awesome. Great. Chalo. Let's go ahead. Let's go ahead now and let's go to basically the types of different forces and other things. Okay. Now that we have understood how to calculate work, etc., by integration or by constant force, so it's time that we see the 2 different types of forces based on how they perform work. Okay, how they perform work. All right. Hello, Aerospiral Lightian. Welcome, Bacha. Welcome, all my lovely warriors, to the lovely JEE English channel. See, guys, let me give you a beautiful example. Imagine I have a surface like this. I have a book. I could have taken some other book maybe. Wait a minute. Okay. I take a book like this. This is a box. This is a box. Okay. And what I do is, it's right now this corner of the book, I want to take it to this corner. One option is I slowly push the box like this. I push the box like this to one corner, and then I push it like this and it reaches here. I can feel the sound of friction. I can feel the rubbing, that screeching effect as this body rubs against this particular book. And definitely friction is acting against my push. As I push it here, friction does some negative work. It is acting against my push. And when I push it here, then friction is acting opposite my push and it does some work in this process. Let's say it is 10 joules, negative 10 joules because it is opposing, so negative work. So let's say it is negative 10. Keep this number in mind, negative 10, keep it in mind. Now I take this same thing, but this time I push it here and then again I push it here, then I push it here, then I push it here, and then I push it here slightly, then I push it here, and then I bring it over here. Do you think the friction will do different work or the same negative 10 joules? What is your answer? Will it be negative 10 or will it be slightly more negative work? Hi Avanashri. Welcome, my dear lovely warriors. Think about it. I was moving it more this time. I was moving like this, then move like this. Every time I can feel that sound of rubbing against the body. I was moving like this, then I moved it like this, then I moved it like this. It has worked for a longer duration. It has sucked away more of my energy. It has taken a lot of effort for me to perform the same action, although I moved from the same initial point and reached the same final location. Definitely, it is going to be different. So, even though my final destination, oh my god, that reminds me of the movie, even though our initial to final displacement was same, but the same friction does different work if I take it like this versus like this, or if I take it like this and like this. Every time it ends up doing different work. Correct? But you know what? Now let's take another example. The same box, I'm holding it here near my face. I lift it up and I bring it here. I lift it up and bring it here. Gravity was acting on it, it did some work. Instead, I took it like this, I lifted it, brought it here, lifted it and taken it here. Same location, finally, but along a different path, maybe like this, and like this. You know what? Gravity will end up doing the same work. I might be doing different work, that's another story, but gravity still ends up doing the same work. If I do 10 joules here, 0 joules here, okay, 0 joules here, 10 joules here, gravity. So here also it will do 10 joules. Here also it will do whatever joules. So it will not be affected by the path which I take. It will not be affected by the path which I take. Just imagine this. See, I go like this and I go like this. Gravitational force always will act in this direction. Let's say the gravitational force was 20 Newton. Here also the gravitational force is 20 Newton. Let's say this was 3 meters. Let's say this was 4 meters. In this part, can you see the gravity did not do work? So in this part, it did basically 0 joules of work. Here, gravity has done some work, 4 into 20, which is basically 80 joules. So total work done by gravity would be 80 joules. Total work done by gravity will be 80 joules. Instead, what I do, I go 1 meter here. Okay, I go 1 meter here. Then I go down 1 or let's say 2 meters down. Then I go 1 meter here and then I go 1 meter down. Then I go 1 meter here and then I go 1 meter down. Isn't it the same place? 3 meters I have gone left, 4 meters I have gone towards the right. I have gone in a zigzag, zigzag, zigzag manner. You will notice in this particular process, okay, all the times when I was going horizontally, I would have done 0 joules of work. All the times I was going horizontally, I would have done 0 joules of work. Why? Because force is down and displacement is horizontal. Every time I was going down, I would have done some work by the gravity. This was 2 meters. 2 meters into 20 Newton. 2 into 20 is basically 40 joules. Here I have gone by 1 meter down. So 20 Newton multiplied by 1, which is 20 joules. Here I have again gone 1 meter down. So 20 Newton into 1 meter, which is again 20 joules. If you calculate the total work done by gravity, 40 plus 20 plus 20 is again 80 joules. So even if I take a different path, it is still 80 joules. Now you can have a curve, obviously, you can have a curve like this and you can reach here. This curve, you can think of it to be made up of infinite small steps. Small steps, right? You can think of it like small steps like this. So obviously you can dissect it and you will still see the answer to be the same. So work done by gravitational force does not depend on the path as long as my initial and final locations are fixed. No matter how I reach, gravity ends up doing the same work. Is it understood? But friction is not like that. Friction will say, you take a longer path, I will end up doing different work, and feel the rubbing to be happening for a longer duration. And in nature, there are these two types of forces which depend on the path or do not depend on the path. Accordingly, they have been classified as conservative versus non-conservative. So just like gravity, there are many other forces, guys. So for conservative, you have gravity, electrostatic forces. Even you will see your spring and elastic force. Spring and elastic force is conservative. Even your buoyant force is conservative. Even your constant acceleration pseudo force is conservative. Constant acceleration pseudo force is also going to be conservative in nature. All these are examples of conservative forces where the work only depends on the initial and the final locations, not on the path taken. Whereas in cases of non-conservative forces, examples like friction, static or kinetic. So friction is there. Even air resistance or drag. Even viscous force, when you move something in a liquid, it offers a viscous force. Like honey is said to be viscous because it does not flow easily. There are some internal forces within that honey which stop the free-flowing nature of a liquid. So that is viscous force. You take a tomato ketchup and you spread it, it does not flow infinitely. It does not spread on the floor completely because it is highly viscous. But if you pour water on the floor, it spreads for more area because it is less viscous, it can flow easily. So viscous force opposes the flow of the fluids, that is viscous force. Okay, all these are examples of non-conservative forces, even for that matter, tension and normal as well. Tension and normal also are non-conservative in nature. Okay, is that clear, everyone? This is like your path function and state function. How many of you felt that? I think Harboran said it already. Yes, this is like, this is path function, this is state function. Somewhat similarity in the physical chemistry part. Cool? Everyone with me? Awesome, awesome. So, my dear warriors, what are the different things which you should know in conservative and non-conservative forces? Work done is independent of path in conservative. Work done in a round trip will be obviously zero. Think about it. If I go from here to here, or wherever I go from here to here, both the work will be the same. So W2 will be equal to W1 for conservative. Similarly, imagine somebody starting from a point and coming back to the same point. Obviously, the total displacement is zero, so the work done will be zero for a round trip. Energy will remain conserved. That is why the name is conservative. See, these forces are good people. Electric force, spring force, elastic force, gravitational force, buoyant force. They can store energy and they can give it back also. It's like your friend, if you give money to him, he probably keeps that money, and when you ask him, please can you give it back, he will give it back to you. So hence the name conservative. But these are evil people. Some classmates of yours, if you tell them, can you please keep this with you, I'll take it later on, that thing will go puchuk, gayab, done, it's lost. So they are non-conservative, they are not going to conserve it. Friction, air resistance, viscous. If you do some work and you expect they will give it back to you, they'll be like, sorry, who are you? Friction takes away that energy, that's it, it's lost to the surroundings as heat. It does not give it back. Hence, that's why the name non-conservative in nature. So hence, you will see energy remains conserved and the work done is recoverable. It's like your loyal friend. It's like your loyal friend. Okay, I hope this is clear. We'll see this point later on, about the fifth point, it will come later on, don't worry about it. Same way, non-conservative, work done depends on the path. So obviously, if I go like this, maybe the work done may be not equal as compared to going like this and coming over here. Obviously, this is a slightly different path, so these work will not be equal. Also, you will see that if I go a round trip over here, the work done will not be zero. Okay, energy will be lost to the surroundings as heat, and the work done is not recoverable. You cannot expect it to give it back to you. Hence, non-conservative force. That's the name given to it. Let's see some examples. Let's see some examples based out of it. Imagine there are some points A, B, and C, and let's say D, and it is given to you like this. This is the arrow mark. Question is, what is the work done from A to D if each of these things are given? This is 5 joules, this is negative 2 joules, this is 3 joules. Okay, some points are marked and it is also mentioned the forces are conservative. The forces are conservative in nature. So question is to find the work done from point A to point D. Let's see if we can figure this out. So glad, Luna, I made it very easy for you. That's the whole point of making you attend these classes, to make it easy for you. All right, so let's start. From point A to B, guys, work done is 5 joules given. From point B to C, it is, not given. It is given from C to B. C to D is given. A to D is asked. I can think as if instead of going from A to D directly, from point A to D directly, I can reach an indirect way from point A to point D via B, via C, and then to D. See this out. Via A, via B, via C, and then to D. Both the paths should have the same work. I hope this makes sense to all of you. So I can say work done between A to D directly should be indirect way also. So work done from A to B plus work done from B to C plus work done from C to D. What is the work done to go from A to B? It is clearly mentioned 5 joules. What is the work done from B to C? C to B is negative 2. So B to C will be positive 2. Will be basically positive 2 because that was negative 2. What is C to D? C to D is already mentioned as 3 joules. So 5 plus 2, 7, 7 plus 3, 10. So hence the answer is 10 joules. Hence the answer is 10 joules. Yep, very good. Janvi, the effort will be to complete the chapter, but we never know. So we are just making sure that you understand every single concept. Great. So that was conservative and non-conservative forces for you. And yes, let's now slowly go towards the concept of energy, potential energy, and the conservation. And after that, we'll be also coming to work kinetic energy theorem, etc. I think it is there. Yeah, later on. Okay. Okay. Yes. Let's go to energy. Energy is basically capacity of doing work. I have more energy means I have something stored in me, and it allows me, it gives me the privilege that, okay, I can do some work on something. Sometimes I might possess that energy because of the situation or the state in which I am placed. So energy is basically the capacity to do work, and there are different forms of energy. Like for example, mainly you classify it as kinetic energy and potential energy. Kinetic energy is the energy which the body possesses because kinetic means motion. So the body possesses it because of the motion of the body. For example, I take a ball and throw it towards you. The body has kinetic energy because it is in motion. How do I know it has energy because of motion? Because if it hits your face, obviously you will get hurt. Then you will be like, ha sir, what you said is right. Sorry, no doubt. You will be like, yes sir, energy is there. You know it will impact you. There are many other ways in which kinetic energy is there, but you might call it something else, like energy of motion, like throwing a ball. Mechanical kinetic energy is again the same thing, guys. Electrical energy, sound energy, thermal energy. So thermal energy, meaning something is hot, means the molecules inside it are vibrating, tuck, 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 they are rotating, they are moving. So if you increase the temperature, the motion will increase and you feel that it is hot. But actually what is happening is the kinetic energy of that object or the particles are increasing. So you perceive it as thermal energy. But at the end of the day, it is kinetic energy. I am talking to you. Sound is reaching you. What is happening when I am talking? The vibration spreads in the medium. The air molecules start vibrating. Tuck, 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 tuck. They start vibrating. They propagate the sound everywhere. So when these molecules vibrate, and they send in those sound waves everywhere, so that vibration involves the motion of the particles. So that is also kinetic energy at the end of the day. So you can see kinetic energy in different forms, okay? But you know, at the end of the day, at molecular level or particle level, it is motional kinetic energy, or particles motion causes that makes that particle possess the kinetic energy. The second type is the potential energy. Because I am in a situation, I have ability to do something because of my situation. I am inside IIT campus, that's why I am eligible for very good placements. So I have more potential energy. I am not in such a great college, so I have less potential energy. So maybe I might not get placement in a very good company. So less potential energy. So same way, if an object or a system, because the manner in which it has been placed, has ability to do more work, it is said to be having more potential, capability type of energy. And it is again in different forms. Like you take two masses, leave it, the masses will attract towards each other. So I will say this masses had potential energy gravity wise. If I take two charges and leave them and they repel, I will say they had electrical potential energy. I take a spring and pull it, leave it, it comes back. I will say it has elastic or spring potential energy. If I take two magnets, leave them and I see they get attracted, so I say yes, they had magnetic potential energy. So just like kinetic energy can be seen in different ways, even potential energy can be seen in slightly different ways. Is this bifurcation clear? The broad classification? Everyone give me a thumbs up. Very good. So talking about kinetic energy, which is the energy which is associated with the motion. The symbol for that is K. It is nothing but half m into v square. As simple as that. Half m into v square. It is also a scalar quantity. No need of direction. Number 2, the unit is just like work. So it will be either joules or basically ergs. Half mv square is the formula. This kinetic energy is also related to the momentum. You can see its relationship very easily, useful in modern physics also. I can just multiply it by mass and divide it by mass. So what happens is this mv square, I take it together. Mass into velocity is nothing but momentum. So p square by 2m is the kinetic energy. Some books also rearrange this and write it like this. P square is 2m into k, or momentum is root of 2 times mass times kinetic energy. So this is how momentum and kinetic energy are related to each other. momentum and kinetic energy are related to each other. Okay, simple question guys, let's see if you guys can solve this. If momentum increases by 50%, then kinetic energy dash by dash, will it increase or decrease, and by how much percentage? That is the question. Cool. Let's try to solve this. So first of all, we know that kinetic energy is 100% related to the momentum, and the formula for that is p square by 2m. So if I take initial momentum as p, initial kinetic energy as k, then think about the final values. Momentum is increased by 50%. So the final momentum will be the old momentum plus 50% of p. 50% of p is basically 0.5. Hence it becomes 1.5 p. Oh. So what about the final kinetic energy, if I call it as k1 or basically k prime? That final kinetic energy will be final momentum square divided by 2m, but final momentum is 1.5 times of p. 1.5 times of p. So this square, 1.5 square is 2.25 p square by 2m. But wait a minute. I just know what is p square by 2m. What is this value p square by 2m? Just observe this. P square by 2m, guys. That is old kinetic energy. So the new kinetic energy is 2.25 times the old one. Is 2.25 times the old one. Perfect. So we want to find, obviously this answer will be increase. Now the question is how much percentage will it increase? So the percentage increase in the kinetic energy will be the final minus original upon the original multiplied by 100. The final value is 2.25 k minus k upon k multiplied by 100. Perfect. K cancels. 2.25 minus 1 is 1.25, is basically 1.25 multiplied by 100. So hence it will be 1.25 into 100 is 125%. So 125% is the answer. Not 25%, 125%. Be careful. Yeah, it is 125%. Yes, kinetic energy will change more because it is related to the square of the momentum. Be careful about it. Yes, very interesting question. So what we just did, old kinetic energy, we know the formula. We just saw it. It is momentum square by 2m, So the new momentum will be 50% more. So if old momentum was p, add 0.5 to it, because 50%, it will become 1.5. So the new kinetic energy will be the new square of the momentum by 2m. You substitute 1.5 here. Square of 1.5 is 2.25. But p square by 2m was k. So that is old kinetic energy. So the new one is 2.25 times more, 2.25 times the kinetic energy before. So to find the change percentage wise, you always take the new and the old, find the difference, divided by the original, and then multiply by the 100. So when you take the difference, k cancels. 2.25 minus 1 is 1.25. Multiplying by the 100, shift the decimal by 2 places, 125%. Clear? Is it understood? Okay. Great. So similarly, you can solve other questions also. Decreased by 50%, increased by this, decreased 5 times, increased root 2 times. Hai na? So Nihash, if the momentum is decreased by 1 by root 2 times, so old momentum is p. So the new momentum will be p minus p by root 2. So accordingly, then square it and then find the new. All right. Now let's go to the main work kinetic energy theorem. This is very, very important. So I'll tell you what this is exactly. Work and kinetic energy theorem. See, when there is a body, there are multiple forces on it, and there could be even internal forces, by the way, within the body. All these forces might change the shape, size, it might move the body, etc. And as a result, the body might gain or lose some kinetic energy. So this theorem says that the work done by all internal and external forces on a system changes the kinetic energy of the system. This is the simple way of statement of work kinetic energy theorem. So I can say maybe, there is some work done by the external forces. Maybe there are 2, 3, 4, 500 forces. So I'll put a summation symbol to signify work done by all the external forces. Maybe there are forces within the system. So work done by all the internal forces as well, the sum of all of it. This will change the kinetic energy of the system. So there will be some kinetic energy finally, there will be some kinetic energy initially of the entire system. That means I'll put summation. Why summation? The system can be made of 2, 500 bodies also. So you add all the kinetic energies of all the bodies or particles. You find the difference, that is your change in the kinetic energy of the system. Changes the kinetic energy of the system. This is basically your work kinetic energy theorem. This is basically your work kinetic energy theorem. Very simple. It makes sense. Let's go back. Let's go back. If you don't believe me, let's go back. Here we go. Let's go back to this question. Do you remember this question which we solved some time back? This lift was going up with constant speed, mass was kept on a rough incline, it was not moving. You had to find the work done. Guess what? The answer came out to be 0, and it had to be 0, even if we did not do this. But at that time, we did not have the knowledge of work kinetic energy theorem. That's why we were not able to say it directly. But now, proudly you can say, sir, I know the answer even before the solution. Because notice the body was going with a constant speed. Constant speed means what? Kinetic energy never changed. So change in the kinetic energy is 0. So total work done by all the forces was actually 0. Such an amazing application, right? Similarly, even the next question, where this string or this rope was pulling this block up with some acceleration. So in this process, obviously the body has gained some speed. So there is a positive change in the kinetic energy. So hence the work done will also be positive. Just for my sake, satisfaction's sake, let us just probably, relook at the same problem. Let's just probably relook at the same problem. Just imagine it starts from rest, it accelerates, and at 2 seconds it gains some velocity. This velocity will be u plus at. Initial velocity is 0, acceleration is 2, time is also, I think, 2 seconds. So this will come out to be 4 meters per second. Okay. Let's try to find out how much is the change in the kinetic energy. Change in the kinetic is final minus initial. Final is half into mass. Mass is 5 multiplied by 4 square. Initial is half into mass. It was at rest, so 0. So 4 square is 16. 16 by 2 is 8. 8 5s are basically 40. 40 minus 0, which is just 40. That is the change in the kinetic energy. So remember, whatever is the change should also be the total work done. So hence the total work done should be 40 joules. And guess what? We have got the answer also as 40 joules. This just shows how work kinetic energy theorem can solve the problem, reduce the length of the problem significantly. Can reduce the length of the problem significantly. Isn't it amazing? Luna, it is going to go on for a long time. Yep. Crystal clear? Okay. There could be more applications of work kinetic energy theorem in many places. Let me show more to you. Where did it go? Yep, this was the work kinetic energy theorem. One more example, classic example. Okay. So, guys, there are some questions where the position will be probably a function of, time. Okay. X coordinate is changing, but it is not a function of, the position, but rather it is a function of time. So in such case, how to do it? For example, velocity is 3t square. Okay. And let's say I give you a time interval and tell you in the first 2 seconds, find the work done. I'm asking you find the work done in the first 2 seconds, and let's say I give you the mass also. The mass of the body is let's say 2 kg. Just taking some random values. Okay, let's see how to do this question. Now, for solving this question, there are multiple ways. Because the velocity is changing with time, so 100%, their acceleration may be different at different time, and maybe even the force is different. So maybe it is a variable force problem. So I will think like this. Okay, can I find the acceleration? Well, acceleration is derivative of the velocity. So it will be derivative of 3t square with respect to time. So the acceleration will be 3 into derivative of t square is 2t. So acceleration is 60. So if acceleration is 60, can I find the force? Of course, force is mass times acceleration. Mass is 2, acceleration is 60. So hence force will be basically 12t. Oh, that's what it is. But the problem is I have to find the work, and work is integration of force with respect to displacement. When I put force value as 12t, I cannot integrate it with displacement because this ds will now become dx. Do you see that? I cannot integrate it with respect to displacement. That becomes a problem. I hope this is absolutely clear. I hope this is absolutely clear. Correct? So we'll have to, either convert dx into time or time into dx. So what you generally do in such questions is, you will have to find time in terms of x, meaning you have to integrate velocity, find x coordinate as a function of time. Is just going to make the problem very lengthy. It's just going to make the problem very lengthy. So I don't want to do all this. Avoid this. Rather, what you do is, okay, I know the speed, I know the mass. Can I find the initial kinetic energy? It will be half into mass, which is 2, into speed. So 3 into 0 square. 0 into anything is 0. So initial kinetic energy is 0. Final kinetic energy, can I find it out? Half into mass into speed. 3 into time, put it as 2 seconds. So 2 square. 2 cancels. 2 square is 4. 4 3s are 12. So 12 joules. Oh, perfect. So I have to find the work done. Work done is change in the kinetic energy. So final is 12. Initial is 0. So the answer is directly 12 joules. Imagine how much nonsense and time I have avoided wasting. I've just avoided all this nonsense. It is unnecessarily lengthy. It was not needed. Work kinetic energy helped me solve the problem in a very simple manner. Can you see that? Yes, I'll be helping you with VRD-EEE, but not now, later on when the time comes. First, let's complete the syllabus, right? Let's complete the syllabus. Yep. So once the syllabus is complete, then it will be easy. Cool. Shall we go ahead, guys? Right? Yes. Oh, sorry. I missed that v square, is it? sorry. Oops. So this would be 6 square. Yep. This was 2 square 4, 4 3s are 12. So this will be 144. So this will be 144 minus 0. So 144 joules. Silly mistakes. This happens. Great. So we have done till kinetic energy, work kinetic energy theorem. Okay. And work done by variable forces, conservative forces and all of that. Now let's just talk about potential energy before we go for a break. Okay. Let's just see what potential energy is and then we'll go. Menti sessions, why am I not conducting? I can, but unfortunately it takes a lot of time and very few questions happen, and plus the time is less. So usually, Menti sessions are okay for 9th and 10th standard. For 11th and 12th, usually students don't like Menti sessions. That's the reason. Okay. Once in a while is okay. Once in a while we all have fun, but can't take it regularly. But yeah, maybe someday I will take it on some occasion. All right. So let's talk about potential energy. Like I said before, anything and everything which has capacity to do work because the manner in which it has been placed is said to have potential energy. So I take this particular book like this and I'm holding it here. I know it has ability to do work. My hand is the culprit, it is stopping it. If I leave my hand, immediately it starts moving down. It had ability to perform work. So this book had some energy, potentially. And this was only because of gravitational pull. If Earth did not pull it, it would not have gravitational potential energy. If I move it somewhere else, it has a different energy because I know if I leave it from here, it will get more energy by the time it comes down. So a book here versus a book here has different amounts of energy. So the situation, the state, the condition decides whether it has more or less potential energy stored in it. Now there can be different forms of potential energy. This one has gravitational energy. Right now, gravitational potential energy. If it were charges, it would have electrical potential energy. If it was a chemical reaction, it was stored in that battery. If that chemical reaction happens, that chemical energy had that ability to perform some work. That's what happens in your electric vehicles. Lithium ion, right, cadmium, all these cells are there. There is a chemical reaction which happens. So chemical potential energy is there. Similarly, you can have magnetic energy. You take a bow and stretch it, the arrow when released, the potential energy in that rope or that elastic string is utilized to propel that arrow. So elastic energy. You take a spring, if you hit it with some object, that object's energy is absorbed by the spring, it stores it and it can again give it back also. So spring potential energy is also one of the forms. Okay. Now this potential energy, some additional pointers are there, we'll just come to it. Potential energy is always defined for conservative forces only. What do I mean by that? Luna, I'll give you a break just after this potential energy. This is the last thing before the break, then we'll have a small break, okay? Don't worry. This is defined for conservative forces only. Why conservative forces? Let's just go back a little bit when we discussed conservative forces right over here. If you notice, all these forces are good people. They are recoverable work forms. If you bring it back to the same place, work done is zero. Whatever you give is given back. This is not. So you will never hear the word like viscous energy, tension energy, normal energy, air resistance energy, frictional energy. Never. But you would have heard spring, elastic, electrostatic, even buoyant force also can store energy, even conservative pseudo forces can store energy. So you will see that potential energy is only defined for conservative forces only. Is this point clear? Why it is so? Did you also understand the first point? Okay, so the first point, important word was energy possessed by a body by the virtue of its position or the condition. It is only defined for conservative, only for conservative. Last one, this is a relative quantity, meaning, see, I have asked this question to many people. If this is the ground, there is a box here, this has 0 joules of energy, or it can be 2 joules of energy or something else. What do you think? Is the potential energy, gravitation wise, of a box on the ground surface, is it 0 or something else? Soumya, I just said that conservative forces do 0 work, no? In a closed path. So while going, if it does positive, it will do negative while coming back. So that work done is recoverable. So it conserves the energy. So whatever it gives, it takes back. Whatever you take, it gives back. So same way, I can say all these forces like electric, gravity, elastic, spring, they are conservative in nature. Only them, you can see, potential energy is associated with them. Like the words like gravitational potential energy. All these words only are associated with conservative forces. But never will you hear the word frictional potential energy, because they cannot store only. Got it? Yeah. So the answer is, it is not necessarily 0. It can have any joules of energy. Imagine if I take this block slowly from here to here. Okay, slowly from here to here. One person says, sir, listen, this has 0 joules of energy, sir. When you reach here, it has 20 joules of energy. Okay. Another Champa says, no, sir, this block has 5 joules of energy already. When you take it here, it has 25 joules of energy. Okay. Then another Pandu says, listen, no, sir, actually this has 20 joules of energy here only. So then by the time you reach here, it will have 40 joules. Or let's say, for example, some Pandu says, no, sir, this is 0 joules. Then this will be minus 20 joules. Similarly, another person will say, no, sir, this body over here has minus 10 joules. Then this body over here will have plus 10 joules. What you see in all the cases is the difference of the energy is the same. The difference of the energy is the same. Usually the symbol for potential energy is U. We don't use P. P is also okay, but we use U at higher levels. So the change of the potential energy everywhere was 20 joules. So what you decide as 0 does not matter. Wherever you take 0, accordingly the other point gets some value of energy. What matters to us is the change of the potential energy. We are never bothered about the actual value of potential. We only bother about the change in the potential energy. Why? Because the change is what gets converted into kinetic. Potential energy is never converted into kinetic, the value of potential. The change of the potential is going to cause a change in the kinetic energy when you use energy conservation. Yep, I hope this is clear. So that is why we can use anything as the point of 0p is called as the reference. Anything can be chosen as the reference. It can be any point. What matters is delta. The change matters. The change matters. I hope this is absolutely clear. Yes, this is a JEE English channel, so obviously JEE. Yes, it's from the basics to JEE level. Atiban. Now, imagine I take a body from here to here like this against gravity. Maybe gravity will do some work. How much work? Maybe it will do negative work because I have taken it on the top. Maybe it did minus 20 joules. That means gravity takes out 20 joules from the body. Takes out 20 joules from the body. In this process, I might be pushing it upwards. So, external force, if you see, is doing exactly 20 joules. So, I can say 20 joules work was done by me all the 20 joules got absorbed by the gravity. So gravity takes 20 joules from the body, which was given by external force. Gravity takes 20 joules from me externally, which was doing work. What does it do with it? Obviously stores it. So gravity, which takes 20 joules from the body, which was given by the external force, will store as gravitational potential energy. So I can say there is an increase of the potential energy by how much? 20 joules. Increase of the potential energy by how much? 20 joules. So from this you get a very beautiful relationship, guys. Can you see delta UG is equal to the work done by the external force, but at the same time it is negative of the work done by the gravitational force. Negative of the work done by the gravitational force. If you put minus 20 here, minus minus becomes plus 20. This is 20, this is 20. This is a relationship which I got. This is not a special case. This is always true, no matter how I move the body. No matter how I move the body, it is going to be always true. Same way, imagine I take an example. Let's say there is a spring like this and I stretch it in this particular manner. Obviously, I have extended it. So in this process, my external force might do some work. Example, 5 joules of work. I am moving it, force in the direction of the displacement. I am doing some positive work. Whatever work I do, who will take it? Spring. Spring will be like, give it to me. So work done by the spring force will then be negative 5 joules. If spring says, give it to me, what does it do? Will it throw it out somewhere? No, it will store it inside it. So the increase in the spring potential energy will be exactly 5 joules. So this relationship always holds, guys. Always, no matter which potential energy you take. So hence, I can definitely probably put it over here only, that is better. So the change of the potential energy is equal to the negative of the work done by that conservative force, whichever conservative force was there, and it is also equal to the work done by the external agent which was pushing it. So this is also another important formula which you should know. See if this is clearly understood. You will see the usage of this in 12th standard in electrostatics and magnetism. Atiban, maybe you might have to start from the beginning if you have missed the initial part. Okay, so beautiful example. Now, like I said, what matters to us is not the actual value of the energy, the change matters. So we define the potential energy formula, spring potential, gravitational potential, etc. as follows. If I take a body up or down by a height h, then the change of the gravitational potential energy is given by mgh. It can be plus or minus both. So actually it's not fair to write it like this. So I can just say that the change of the potential energy will be mgh. It will be plus if I'm going up, and it will be obviously minus if I'm going down. Vertically up, positive; vertically down, negative. If I'm going sideways, then there will be no change. M is the mass being lifted up or down, G is the acceleration, H is the height difference. Okay, clear? So this is the formula for your gravitational potential energy, guys. Plus or minus mgh depending on whether you are going up and down. Similarly, even the spring potential energy, okay, can be found out. It's not that difficult. And that value comes out to be as half kx square. So when it is at the natural length, if I take the reference as 0 joules, this is your 0 reference, 0 reference. So then when it is extended, or compressed by an amount of x, the spring potential energy is given by half kx square. Is just given by half kx square. As simple as that. Okay, very, very important again. You should know 0 reference is taken as when there is no extension. So no extension means it is relaxed. So this will have 0 potential energy. So here potential energy is 0. You compress it or extend it, either ways it will store energy. Here also half kx square, here also half kx square. Don't say this is negative half kx square, this is positive half kx square. No. Whatever you do, it will store in the compressed state or in the pulled or the extended state. It will always be half kx square only. Great. Perfect. Now, since we have done this part, delta U is negative work conservative, there comes a very, very interesting thing. Where we just saw, what is it? Delta U was equal to the negative work by the conservative force. Now, if I take a small change, for a small change, the work done will also be small, the change in the energy will also be small. So instead of delta U, it will just become du, and this work will then become dw, small work done. Work is force into displacement, so I can just say this small work is F into ds. F into ds, ds being the displacement. Perfect. So what I will do, I'll shift this ds down, and this du was here only, and this is minus f, or rather f will become minus du by ds. Again, a very important relationship between our conservative force. This is only for conservative forces. So this is only for conservative forces, not for anything else, because this was also for conservative only, is negative du by ds. This du by ds is called as a very special term. Rate of change of energy with respect to distance is called as the gradient of potential energy. So this is also said as conservative force, I can say, is the negative gradient of potential energy. Whenever you hear the word gradient, it means derivative with respect to displacement. When it is rate of change, it is derivative with respect to time. When it is gradient, it is with respect to displacement. That is the meaning of gradient. So conservative force is the negative gradient of potential energy. Okay, I hope this is absolutely clear. Great. So all this is done. So probably just to show you a simple example of this. If an external conservative force does a work of 17 joules, find the work done by conservative force and the change in the potential energy. Well, we all know that if external force is doing work, conservative force and delta U will also be there. And we know this formula, delta U is work done by external force and is negative work done by conservative force. This is nothing but 17. This is nothing but 17. So delta U is 17 and work done by conservative force will be negative of this 17. So conservative force will just do negative 17 joules. We'll just do negative 17 joules. As simple as that. Okay. Let's do one more question. Let's do one more question coming up on your screen. If I tell you potential energy is 3x square minus 2x plus 5 joules, can you find that conservative force associated with it? Can you find that conservative force associated with it? That is the question. So when you look at this question, you should probably be reminded of this formula. Force is related to the energy with this negative gradient formula. So if energy is given, to find the force, just have to take the derivative with respect to the displacement. Hence, why not write the conservative force as negative gradient of the energy with respect to the displacement, but since it was everything in x-axis, put dx here. So I will get the answer. So minus d by dx of 3x square minus 2x plus 5. So what will it be? Minus 3x square's derivative will be 3 into 2x minus 2 into x's derivative is 1. 5 is a constant, so derivative is 0. So it will be minus 6x plus 2 newtons. So that's the value of the conservative force. Minus 6x plus 2 newtons. No, Kirti, in the question momentum is increased. So p square, right? P square by 2m. Momentum is in the numerator. How can kinetic energy decrease if I increase the momentum? Keeping the mass constant, of course. So if momentum increases, kinetic energy has to increase because momentum was in the numerator. P square divided by 2m. Okay, it cannot decrease. Thank you, Ashwin. Thank you so much. Glad you are new and you are liking it already. So after this, let's go to conservation of energy and all of these principles. So all these things will be done after the break. Let's take a break, 10 minutes break. Okay, let's take a break and return. Okay, we'll continue with it. Yo, welcome back guys, welcome back. I hope I'm audible and visible. A lot of you are new to the channel, I know, and we have done a lot of things till now. Work kinetic energy theorem, potential energy, formulas. Yep, time to move ahead. And if you're new to the channel, make sure you are subscribed and liking the video. That should be your daily ritual. That's your fees for watching the video, liking the video, and be a part of the channel, or else you'll miss all the other important videos. Okay, so time to proceed. Get back guys. Yes, let's move on. Ready? Everyone? Full of fire, V Enthuse Club? Yep. Thank you. And glad you are back, V Enthuse Club. I'm waiting for your reels. I'm waiting for your shots which you're going to put up. So, just like the name suggests, law of conservation of energy, which says that energy is conserved. If you remove energy in one form, it will appear in some other form. If you see any process, it always involves some kind of energy transfer in one or the other way. I throw a ball up, my energy which was stored inside the body is given to the ball in the form of kinetic energy. As it goes, it increases the potential energy. Water falling from a height in a waterfall and falling on a turbine, the gravitational potential energy of the water is converted into kinetic energy of the water, which gets transferred to the kinetic energy of the rotating turbine, which is converted into electrical energy, and the electrical energy can light a bulb. So maybe light energy, maybe rotate a fan, maybe mechanical energy, maybe heat a water, maybe heat energy. So different forms. So every process involves some kind of energy transfer, and you cannot get any new energy, or nor can you destroy the energy in this universe, right? So the total amount of energy in this universe is always going to be conserved. That is what basically this law says. So yeah, no, not late, you just started. Now, many examples, like I said before also, even a roller coaster ride, if you have ever wondered. So while going on the top, it goes slowly because the motor, the conveyor belt, the track is slowly pulling you up, and once you reach the highest point, you have a lot of potential energy. It gets utilized as kinetic energy, and then again potential, again kinetic slightly, and then again you go up, go round. So potential and kinetic energy keep interconverting into each other, right? That is what you will see. Great. So I can say, first of all, I define a new term over here called as mechanical energy, mechanical energy. Mechanical energy, simply put, is nothing but the sum of the kinetic and potential energy. It is nothing but the total sum of kinetic and the potential energies. So the mechanical energy, if I denote it with a symbol of E, it will be nothing but the kinetic energy plus the potential energy. If there are multiple particles, I will put a summation symbol to signify I will add up all their potentials and kinetic energies. So that is the meaning of mechanical energy. If I mean to calculate the change of the mechanical energy, then I have to see how much the kinetic changes by and how much the potential energy changes by. That's how I can find the change of it. For example, say I tell you initial kinetic energy is 2 joules, final kinetic energy is 10 joules, initial potential energy is, let's say, minus 5 joules, and the final potential energy, let's say, is minus example 10 joules. Question is to find the change in the mechanical energy. Let's find this out. It's very simple, it's not that difficult. The final mechanical energy will be final kinetic plus final potential. Final kinetic is 10, final potential is minus 10. So final mechanical energy is 0 joules. Okay, Fair enough. What about the initial mechanical energy? It will be initial kinetic plus initial potential. Initial kinetic is 2. Initial potential is -5. So it will be basically -3 joules. That is your initial mechanical energy. In order to find the change, I have to subtract the two, final minus initial. Final was -3, initial was 0. So hence it is -3 joules. So can I then say that the mechanical energy decreases by a total of 3 joules in this scenario. So the mechanical energy has decreased by 3 joules in this. Oh, sorry. I think I made a mistake over here. My bad. Final was 0. My bad. And initial was -3. My bad. So minus will become plus. So it will become plus 3 joules. So mechanical energy increases. Mechanical energy increases by 3 joules in this scenario. So in this problem, can I say mechanical energy remains constant? No, right? In fact, it has increased. So in this problem, can I then say mechanical energy is basically not conserved? Basically, it is not conserved. So there are problems where mechanical energy may be conserved. There are problems where mechanical energy may not be conserved. So how do I know whether it is conserved or not? One is you actually calculate it, like I have shown over here, and then you see, oh, it is conserved, oh, it is not conserved. But is there a simpler way? Is there another way, another approach to just look at the situation and figure out, oh, sir, mechanical energy won't be conserved in this situation. Mechanical energy here, it will be conserved, it will be constant. The answer is yes, we can find it out. There is another approach to figure out whether it will be conserved or not by using this information, but by looking at some other aspect of that problem. Okay, thank you, Ibrahim. Oh, by the way, I got this outfit from the Vedantu store. You too can buy this Vedantu merchandise, that bags, the shirts and pens, notebooks, Vedantu merchandise. It's there on the Vedantu store. Just check out the description box. You can buy these t-shirts, jackets, so many things are there. All cool stuff. So in a situation where non-conservative forces, even if they are present, don't perform work. In such a case, mechanical energy is conserved. Mechanical energy is basically going to be conserved. Meaning, I can say initial mechanical energy is final energy. That means initial kinetic plus initial potential will be final kinetic plus final potential. This is only true if and only if the total work done by frictional forces, viscous forces, non-conservative forces is 0. This is called as the conservation of mechanical energy principle. Okay, this is called as the conservation of mechanical energy principle. As simple as that. But what if the non-conservative forces are present and they are doing work? If non-conservative forces do work, then no issues. Simply put, whatever is the change of the mechanical energy, whether it is increasing or decreasing, will be equal to the work done by the non-conservative forces. As simple as that. So, say for example, the frictional force, etc., might end up doing some negative work. Let's say it does -2 joules done by friction. This means I can say mechanical energy will decrease by 2 joules. That's all. So if friction is doing -2 joules work, so the total energy will decrease by 2 joules. Somebody is pushing it. It's a normal force, which is non-conservative. So external force is doing, let's say, 7 joules of work. Then the mechanical energy will increase by 7 joules. That's all. So the change in the energy is the work done by non-conservative forces. In such cases, this is when mechanical energy is not conserved. Mechanical energy is not conserved. Keep this in mind. Is this absolutely clear? Definitely squeaks fun, definitely. Ibrahim, I'll be starting probably a new group, but wait a minute, because there is some thing going on about Telegram where the Telegram CEO is arrested. So I'm also waiting for it. But I have a WhatsApp group, WhatsApp channel, not a group as of now. But maybe I will start a new interactive Telegram group very soon. Just give me some time. Okay. Hi Subareddy, welcome. You guys are late or what? Okay, cool. Let's see some problems associated with it now. Imagine there is a box like so of 10 kg and it is moving at 4 meters per second, or let's say 20 meters per second on a smooth table, and there is a spring associated over here, the spring kept over here of a constant of 100 Newton per meter. What will happen is this block will hit that particular spring, and eventually the spring will have maximum compression when it stops, when this box will stop. So there will be a maximum compression in that spring. The question is, how much is this maximum compression? Let's try to solve this question. Now, whenever you get energy conservation or work power energy problems, always make a story in your mind. Yes, you can do the problem via these formulas also, but often making a story in your head makes the problem look much simpler. What do I mean by that? Make a story in your head about the situation of what is happening. There was motional kinetic energy of the box. Spring did not have any energy. This kinetic energy went completely and got stored inside this spring. Nothing was left with the box. Meanwhile, gravity did not do anything, nor did friction work anything, because it was a completely smooth surface. So I can make a story in my head and I can say the kinetic energy of that box got converted into the potential energy of the spring. Kinetic energy of the box is half mv square. Potential energy of the spring is half kx square. If you go by other method also, you will get the same thing. Initial kinetic plus initial potential is final kinetic plus final potential. You will still get the same thing. How? Initially, kinetic energy is half mv square. The spring is not even compressed, so zero potential energy. Okay. Finally, the box comes to a halt when it is maximum compressed. So it will have zero kinetic energy and spring energy will be half kx square. This is same like before. This is same like before. This is exactly the same equation. So you can either use the formula or just make a story in your picture, in your mental picture, and see how every form of energy is getting converted into any other form. That's all. So now you can solve the question. Half gets cancelled. The mass is 10, velocity was 20, and spring constant was 100 and multiplied by x square. So I think I'll just cancel one 0 over here. So therefore x square will be 20 square divided by 10. So therefore I can say x will be 20 divided by root of 10. That's it. 20 divided by root 10. That's the answer. Is that clear? So if you want, you can leave it like this, or you can also rationalize it. You can write 20 as 2 into 10 divided by root 10. So you can see root 10 will cancel. So you will get 2 root 10 meters over here. As simple as that. It's one and the same thing. Cool? Everyone understood how to solve this? Here, mechanical energy was definitely conserved. Let's take another example. Imagine there is a pendulum like this. It is attached over here. This is the length of the string. This mass is m. And what happens is this mass slowly comes down and it acquires some velocity right over here. It acquires some velocity right over here and it becomes perfectly vertical. Question is to find this velocity and assume that it was left from rest in this particular position. Now to find this velocity, also given to us is this particular angle, which is going to be theta. Let's try and solve the problem first. First of all, see guys, in this problem, let's understand whether mechanical energy is conserved or not. Because for the mechanical energy conservation process, there should be no non-conservative forces performing work. Evil forces, friction, normal, tension, viscous, air drag, etc. On this mass, in this pendulum, there is gravity and there is tension. The good part is gravity is conservative. See, gravity is conservative force, but the problem is tension is non-conservative, force. That's the problem. So you might think for a moment that maybe, may not be, mechanical energy will not be conserved. So I cannot say potential energy is getting converted into kinetic energy. So I'll think again, but wait a minute. For this pendulum, the tension force will always be perpendicular to the displacement at any instant. In that circular path, think about it. In that circular path, the tension will always be perpendicular to the displacement. That means the work done by our tension force is always going to be zero. Oh, so it's like a virus which is present inside the body, but it is dormant, it is sleeping. It's not yet awakened. So if that virus is still, I am also okay, fine, no problems. You stay cool. I will not be affected. I will not get any fever or I will not fall ill. So here also the tension is dormant. It is not doing work. So I am safe. I can apply mechanical energy principle, conservation principle. So mechanical energy is definitely conserved. Awesome. So what kind of energy got converted into what kind? From here to here, it had potential, it got converted into kinetic. So there is some height difference associated. We need to figure that out. So for that, I'll do a small geometrical construction like this. Now, if this is L, this height over here clearly will be L's cos theta. L's cos theta. This mass has gone down by this much height. Clearly, can you see that? Everyone, it has gone down by this much height over here. This height will be this. The total, remember, this total was L. This whole thing, right from the top till the bottom was L. This was L cos. So it will be L minus this L cos theta. So that height will be L into 1 minus cos theta. That's the height. I will need it for the calculations. So I will just say that the potential energy of gravity got converted into the kinetic energy of that particular mass. Potential energy was mgh. Kinetic energy was half mv square. Mm cancels. But you know what? I know the height already. It is L multiplied by 1 minus cos theta. So that is half into v square. Take v value. It will be root of 2gl 1 minus cos of theta. That's the answer. That's the value of the speed over here. Is this absolutely clear? Definitely not. IPL News, how can you complete whole math syllabus in 1.5 months? What kind of question is that? Not possible. Okay, everybody with me, right? Shall we go ahead to the next kind of question? coming up on your screen. Get ready for it. All right. A spring is compressed and stores U energy if it has to be further compressed by the same amount, how much more work needs to be done? How much more work needs to be done? That's a question, guys. Let's see if you are able to figure this out. So, imagine our spring was already compressed by some amount x. The energy stored in it is U. If I further compress it by x, that means our total compression would be 2x. It will have some new energy, I will call it U prime. So I want to find in this process how much work was done externally. That is the question. How much work was done to bring it from here to here in this extra compression process. If you are perfect in physics and chemistry, still understanding, solving problems takes time. You can't do perfect mathematics in 1.5 months. It takes more time. So give it 2 to 3 months, spread it over, and what happens is when you only do mathematics for 2 months, okay, then you think that you know physics and chemistry perfect, but then you will start forgetting things and then you need to revise. So when you again start revising in the month of November or whatever, December, then you will miss out on the crucial time of doing full syllabus mock test. So it's better to spread it out, go systematically, step by step, do all the high weightage topics initially and all the required topics, and then simultaneously also keep in touch with physics and chemistry so that you will not face difficulty in the month of November. That's what I would suggest. Okay, even if you do 70%, 80%, that will be good by November or October, right? Okay, so in this situation, the original potential energy stored was half k x square. The final energy stored will be half k, extension or compression is 2x. So the work done externally, remember, is the difference of the potential energy, final minus initial. So final was half k into 2x whole square. Initial was half k x square. So it will be half k x square. 2 square is basically 4. 1 square is basically 1. And half k x square was u. So 4 minus 1 was 3. So 3 times of u. So external work done was 3u. Okay, if you did not get it, no issues. I'll write it over here, half k x square into 3. This was basically u, that is 3. So 3 times of u is the external work done. That's the answer in terms of u. Very good, awesomeness. Let's move ahead to another beautiful question coming up on your screen. You take a small block of mass m and it is at rest, and you release it from some height, and there is a spring over here of constant k. Question is to find the max compression in that particular spring. The question is to find the maximum compression in that particular spring. Let's try to do this question. Okay, everyone? Now, in this problem, lot of you will think, sir, it is so simple. This mass has gravitational energy. Yes. When it compresses, it has spring potential energy. So the gravitation got converted into spring. Perfectly fine. There is nothing wrong in that. So let's start with this. Initially, the mass had gravitational potential energy. It got converted into kinetic. But again, that kinetic got converted into spring potential energy. So indirectly you can say the gravitational energy got converted into spring potential energy. Is that right? So one will say the gravitational potential energy is mgh. Spring energy is basically half kx square. Maximum compression, when it happens, it stops, the block stops. It has compressed is enough. It is no longer compressing it. So it has lost all its motion. But this equation is not correct. This is wrong. Can you tell me why it is wrong? Nishant, definitely. I will make one video. Can you tell me what is wrong in this particular equation? There is something definitely wrong in this equation. And I'll tell you, probably after drawing another diagram, you might be able to figure that bit out. I'll just show the next situation over here. The spring is compressed maximum. This block has reached here, okay, like this, and this is that compression which we have to find. Think and tell me, why is this equation wrong? Quickly analyze the problem, guys. Quickly analyze the problem. You will realize why this equation is wrong. There's some mistake in this. Yes, real English, Ansu. Very good. So there is a extra height which we have not taken into account. The potential energy was not just mgh. While it came down also, it lost more gravitational potential energy. Hence, this is not just mgh, it is mgh plus x. mgh plus x. Is that right? Everyone? Yep. So that is very, very important, and that's the common mistake. This has also come in JEE mains, by the way. So now we can solve the problem, but let's rearrange the equations slightly. So 2mgh plus 2mgx is equal to kx square. Just taken 2, opened up the brackets, rearrange the term, kx square minus 2mg multiplied by x minus 2mgh is equal to 0. Now this is a quadratic equation, like you can see. This is a quadratic equation. Quadratic equation obviously has two roots, so let's find the roots now. So x will be minus b plus or minus then 2 times of a is over here k, minus b means minus of 2mg, okay, plus minus root of, a lot of things will be there, b square, which means 4m square g square, minus 4 into a, which is k, into c, which is negative, so makes it plus 2mgh. So let's see what happens. 4 I can take it outside, minus minus becomes 2. So 2mg plus or minus 4 is taken outside, becomes 2 root of m square g square plus 2mgh the whole thing divided by 2k. Obviously you can see over here this 2 and this 2 cancels. Now whether I should take the positive or negative, everybody will like, sir, take positive. Why? We are used to taking positive. Don't be like that. Don't just go, oh, positive, negative, ignore. No, think why you should take a root. See, the value of this quantity will be 100% more than mg, because m square g square plus something. Had this quantity not been there, then root of m square g square will be mg. So positive will be mg plus mg, but negative will be mg minus mg. But when there is something more, this whole thing is more than mg. So positive value when chosen, it will be mg plus something more than mg. But when you take the negative sign, it will be mg minus a more negative number. A more bigger number, which will make the answer as negative. But x can't be negative. How can x be negative? X is chosen. If x is negative, that means instead of compression, it is extending. The assumed direction is wrong. So it is not compressing, it is extending, which is not correct. So that is the reason why I will ignore the negative root and I will take the positive root, and x will then be, mg plus root of this whole thing divided by k, m square g square plus 2mghk. That is the answer. Because since x has to be more than 0 for compression and x less than 0 means extension, which is not correct, Hence I have ignored that negative root. I have chosen the positive sign solution. Is it clear? Yep. Nishant, you can start concentrating on your boards, from November onwards. Don't ignore it completely. Usually I say that concentrate more on your 12th syllabus. So simultaneously do NCERT based questions also. And keep giving your, mock tests or whatever, prelim exams or pre-board exams, especially in the month of December. If you can avoid few, it's okay, but don't ignore it completely, but don't be invested too much in it. After Jan attempt, then you can go full-fledged. If you understand the concepts thoroughly, trust me, you can do really well in boards. Okay, there are only few things which you need to memorize, but those are like those subject-specific things like English and computer science. Those subjects you might have to invest a little bit time. No, Sanjay, portions won't be completed by September end, not possible. Okay, still lots to do. All right, great. So this was the answer for this particular question. Beautiful solution. It had so many hidden concepts involved over here. Okay, everyone. Shall we go ahead to the next question, guys? Ready for it? Everyone? Ready for it? Okay, chalo, let's do next question. A lot of spring based questions being done. Imagine there is a spring like this, and right now it is in its natural state, it is relaxed. This is K, this is M. You release it, you release this particular mass. This mass will go down, stop, and it will come up. It's not just like going to go down and stop. It's going to go down, come up, go down, come up, and it will keep on oscillating back and forth. You can see that right over here, probably in our FET simulations too. Maybe somewhere we might see that simulation somewhere. It's a very interesting one. Hopefully it comes up. See this. Masses and springs. Beautiful simulation, guys. Have a look at this. I'll take a mass, hang it over here. See, it keeps on going up and down. But it stops eventually, maybe because of frictional forces. If friction, damping is there, it will stop. But if it is not there, then it will never stop. So let's get it back over here. Right now the spring is there. Maybe I can see the natural length. This is the natural length. I slowly attach this mass over here at the natural length and release it. It goes up and down. You can see there is a line till which there is a maximum displacement, somewhere maybe over here. This is the maximum displacement, maximum extension of that particular spring. I can also keep that mass at equilibrium if I hold it. Oh my god, I might have to hold it somewhere over here, somewhere in between. If I keep it slowly, arrange it, it probably probably this is the line where the mass remains in equilibrium. You can see that somewhere over there. Are you able to see that? Almost at rest. So we want to find when I release it from here, what's the maximum extension like, that red line to blue line. Are you able to understand what the question is? Everyone clear about this? Let's take that extreme scenario. Let's take that extreme scenario where the spring is basically extended, the mass is over here like this, and when that maximum extension occurs, can you comment about that mass? Can you tell me something about that mass? Okay. That mass, will it be in motion? No, right? It will come to a halt. Maximum extension has happened. So this will be definitely at rest. How do I find this x? Let's think. Which energy got converted into which energy? If you are able to think about it, it will be beneficial. I am releasing it, it has no kinetic energy. It stops eventually, it has no kinetic energy. So which energy got converted into which one? Hi Usha, good evening. I think over there, it had gravitational potential energy. I think it had gravitational potential energy, which got converted into the spring potential energy when it got extended. Just check this out. Kinetic energy was not achieved only. Neither did it have before, nor did it have now. Can you see that, everyone? Perfect. So what is the gravitational energy which it has? Well, just imagine this line. Just imagine this line. This mass is basically how much high as compared to this level. If I take this level as 0 joules of gravitational potential energy, this will have mgh energy. This will have mgh, h being x. Spring wise, it has half kx square energy. X cancels, so mg will be kx divided by 2. So therefore, x will be 2 mg divided by k. This is your max extension. This is your maximum extension. Correct, Harborine. Good evening, Jayakash. Many people will be like, sir, why did you do it with energy, sir? I didn't quite get it. I mean, I thought maybe we had to do it by forces. So some of you might have thought, maybe I will just show the forces on this mass, and one force is basically mg down, and the other force is spring force, which I can take it as ky, y being the extension, of the spring or the deformation. So many people will think, sir, should I not write mg is equal to ky? So from this, y is equal to mg by k, because it will reach equilibrium. Guys, this answer is way different from this answer. In fact, this is double, this is half of this one. Why is it? The reason is, when you release it, it accelerates, and when it accelerates, there comes a time, observe this carefully now, in this problem, when it was at natural length, right? There is only one force on it, which is mg. Okay, there is no spring force, it is not yet extended. As it comes down, then mg still remains, but in the opposite direction, you will see spring force will increase. As it comes down even further, mg will still be there as it is, spring force will increase even further. As it comes down even further down, you will see there comes a moment when mg will be exactly equal to the spring force, Slowly the spring force is increasing and they become equal. And at this moment, you might think the velocity is 0, but that is not the case, because all this while the net force was down, net unbalanced force was down. So actually it was accelerating. Yes, it was accelerating, and at this moment the acceleration became 0. So if it was accelerating all this while, which means right from this position when it was at rest, it was slowly gaining velocity. So don't think when acceleration is 0, velocity is 0. In fact, it has momentum. So because of which this mass won't stop over here. It will go further down. It will go further down. And as it goes further down, then the spring force begins to increase more because of the extension. And instead of accelerating down, unbalance is upwards. So it begins to accelerate in this direction. And because of that, the velocity will no longer increase. Rather, the velocity will begin to decrease. And slowly, slowly, you will see as it goes even further down, the extension will increase even more. The spring force will increase even more. The acceleration might be even more retarding. Velocity will decrease even more. And finally comes a place where this mg and this retarding spring force has become so huge now. So the acceleration is also maximum, and this block basically comes to rest. This is when the maximum extension happens. This is what we have found out in this particular question, which came out to be 2 mg by k. So essentially from here till here is what is basically 2 mg by k. This answer which we found, mg by k, is only from here to here. So just from here to here is mg by k. I hope this made sense to all of you. So at equilibrium, yes, it is mg by k extension, but it won't stop because it has momentum. It has acquired the velocity before, so it further extends the spring until it comes to a halt. This is when the maximum extension happens, which is 2 mg by k. Is it clear, everybody? Understoodo, clearo, perfecto? Yep. Good evening, Grishma. Awesome. Let's go to another question coming up on your screen. Imagine there is an inclined plane, there is a block of certain mass, and this angle is huge. This is, let's say, mu is basically 0.5, and this angle is just 30 degrees, or let's say 37 degrees. This mass is given some speed, okay, let's say speed of u. Because this surface is rough, I know for sure this mass will only travel some amount, and after that maybe it might stop because the friction is quite large, angle is not so much. So maybe it just stops somewhere. The question is, you have to find what is the distance of stopping. After what distance does it basically stop? That is the question. Shall we do this? Let's do this. Okay. Now, the moment I see friction, my eyes should open up. I should think, oh, wait a minute, mechanical energy may not be conserved. Okay. Again, you have two options, guys. You can use this formula, delta is equal to work done by non-conservative forces. But another option is you make a story in your head and then solve the problem. What would be your story? Just think about it. I will say this mass right now over here is at some height. It is at some height. So definitely it has some potential energy gravity wise. It travels some distance s. In this process, it's like you are paying a toll tax to the friction. It's like, okay, I have to go against you. Here, take the tax. Here is my toll, money. This gravitational energy goes into the friction. Friction takes away that. Not just that, even this mass had some speed, so there is kinetic energy also. So I can say that the kinetic energy of the mass and the gravitational energy goes like a tax. Eventually nothing is left over here. neither gravity nor kinetic. Only what is left is the money which has been spent, and it's just gone. It's just gone to the friction. So it is gone against the friction. Friction has taken that energy. So work done by that friction. Okay, that's what I will say. Is that making sense to you? Just check this out. Yep. So what kinetic energy does the mass have? It has half mu square. What is the gravitational energy? mgh. How much tax did friction collect? Frictional force multiplied by displacement. Frictional force multiplied by displacement. Let's find out how much each of these quantities are. Well, if this is 37 degrees, how much will be the height? If this is s, this will be s sine 37. Sine 37. Sine 37 is basically 3 by 5. So 3 divided by 5 into s is basically the value of h. Okay. How much will be the frictional force? Friction will act opposite. That friction will be mu mg. That friction will be mu mg, or just think of it like this, mu n, and this normal will be mg cos 37. Why cos 37? Because normal force will be like this. It will balance mg cos component. So that's why mu value being 0.5, m being m, g being g, cos 37 being 4 by 5. 5 and 5 cancel, so it will become 0.4. So 0.4 mg, which is nothing but 4 by 10, which is 2 by 5 times of mg. So we got these things. So substitute the value of friction as 2 divided by 5 times of mg. Substitute the value of height over here as 3 times of s divided by 5. Rest of the equation stays as it is. So half mu square plus mg into height is equal to frictional force into the displacement. Bring this guy over here. So therefore half mu square will be 2 by 5 minus 3 by 5. Have we done it correctly? Oh, I think I should have taken more friction maybe. Then it would have stopped, because or else it is coming out to be negative. Maybe I should have taken more friction, guys. Let's take the coefficient of friction as maybe 1. Okay, I've just taken some random value over here, as you can see. So maybe this friction is not just enough. This friction was not enough. Let's say mu is equal to 1. Maybe then it will hopefully stop. So in that case, this will not be 0.5. This would be just 1 into mg. So this will be 4 by 5 times of mg. So here also I will put it as 4 by 5 times of mg. So now it is okay. I think now we'll get a positive number. So 4 by 5 minus 3 by 5 will be nothing but 1 by 5 mgs. Mm cancels, so u square by 2 is equal to gs divided by 5. So s will be 5 by 2 u square divided by g. So 5 by 2 u square by g is the stopping distance. Is that clear, everyone? So you have taken the value of mu as 1, not 0.5, in order to just stop it. This is how you can solve problems where even friction is involved. It is not that difficult. It's not that crazy also. Everyone with me? Clear about this? Great. Awesome. Awesome. Very nice. Now, let's go to the next concept, and that is basically your power. Let's go to the next concept, which is the last concept, which is basically the power. Now, power, simply put, is nothing but the rate of doing work. Is nothing but the rate of doing work, how quickly you are doing the work. Rate means derivative with respect to time. So derivative of the work with respect to the time is simply put the power. But you can rewrite it in slightly different forms also, because work is force into displacement, and you can write this as F into dx by dt. Dx by dt is velocity, so you can also write it as force into velocity. This is also the right formula, so I can just block it out. Okay, but if you want to write it in vector form, then put force here, velocity here, and then put a dot product. So power is force dot velocity, or dw by dt, one and the same thing. You can see the unit of power. The unit of power, this is joules, this is second, so it will be joule per second, which is nothing but watts. There is another unit which is called horsepower, and the horsepower is nothing but 746 watts. 746 watts. Also remember, it is a scalar quantity because there is a dot product. Scalar quantity. As simple as that. So these are some basic things which you should definitely know about power. The problems on it are very, very straightforward. Let's do some quick questions on it. Okay, some quick questions on power. Very nice questions. If there is a mass of 2 kg having position given by t cube, can you find the power as a function of time? Can you find the power as a function of time? That is the question. Let's try to do this. Next question session, maybe I will teach circular motion and maybe then I'll go to magnetism. Collision, Ashwin will be doing it in the collision center of mass. That is another chapter, not now. Sir, why are you also taking kinetic energy of the mass in the previous question? So basically, see, this mass had kinetic energy. What then all did it have? It had kinetic and potential. Both of them went against the friction. Both of them were consumed against the friction. That's why I have taken both. If it was at rest, then I would have just taken gravity. If it was just going horizontally, then gravity would not be consumed. Gravitational energy would be same. So that's why I have taken both. Is that okay, Ashwin? Is it absolutely clear? All right. Now in this question, because I want to find power is force into velocity. I don't know velocity nor do I know the force. So I'll find out each one of them. Starting off with velocity. Velocity is the derivative of x. Okay. That means I have to take the derivative of t cube, which means it is 3t square. Oh, perfect. But I don't know the force. Okay, no issues. I know to find force I need acceleration, and acceleration is derivative of velocity, which means it's the derivative of 3t square. So it is 3 into 2t, which is 6t. But force is mass into acceleration. Mass is 2, acceleration is 6t. So it is basically 12 times of t. Perfect. Now I can find the power. Power is force into velocity. Force is 12t. Velocity is 3t square. 12 3s are, guys, 36. So 36 t cube is the power at any instant. We got it. Everyone, is it absolutely clear? Beautiful question. I hope you understood concept of derivatives was involved. Let's do more questions, guys, coming up on your screen. Find average and instantaneous power at t time after a mass m is basically dropped. That is the question. After you drop a mass, it falls down for some time. Find the average as well as the instantaneous power after that time. Let's try to solve this. Another amazing question. Let's draw the scenario first. So this mass is there. This was at rest. It comes down, let's say, by some height, and after it comes down over here, it has some velocity. So it has come down, it has gained some velocity. Meanwhile, the gravitational pull on that mass was always there, which was mg. So question is instantaneous as well as average power. Remember, mg never ever went. Mg force on this mass was always there. I think instantaneous power is very simple. Instantaneous power is just force into velocity. This is the force of gravity. Gravitational force is mg into velocity. But what is velocity? Think about it. What would this velocity be? I have to use kinematic equations to find it. So this velocity will be u plus at, guys. This initial velocity is 0, acceleration is g, t is t. So hence this answer will become mg into gt. So therefore it will be m into g square into t. That is your instantaneous power. That is your instantaneous power. Beautiful. Now the second part is average. Okay, how do I find average? I can't say force into velocity directly. That is instantaneous. So to find average power, I have an idea. I will find the total work done by gravity upon the total time. How much work was done by gravity? Mg and into the displacement. So force multiplied by displacement upon the time. But the problem is h is not given to me. So I will have to think what to do with the height. Height can be found by using kinematic equation again. Height is nothing but, think about it, ut plus half at square. So u is 0, acceleration is g. So guys, this is just gt square divided by 2. So just substitute over here gt square divided by 2. T cancels, g into g is g square. So mg square t whole thing divided by 2. That was your average power. You can see average power is less, in fact half of the instantaneous power in this case. So this clears your concept that how to find instantaneous values versus average values. Is this clear? Definitely GBN, it will help you clear all the concepts. It will help you build that momentum. Yes, once you build that momentum, then you can start solving even more questions, and we'll be having more problem solving sessions. It's not the end of work power energy. We'll be having PYQ session, then we'll be having even more difficult problems, and advanced problems will follow after that. So we'll be having all kinds of problem solving also. It's not the end of it. Keep that in mind. Very good. Awesome. Then there is another concept over here. Which is like you might be given water from a lake is pumped at, for example, 10 kgs per second to a tank at a height of 20 meters. If the motor has 50% efficiency, find the electrical power consumed by that motor. Okay, another amazing question. You might have seen these kind of questions do come in the JEE exam. At a height of 20 meters, and one more thing was missing actually, to a height of 20 meters, and oops, and also speed has to be given. Speed is, let's say, maybe 40 meters per second. Okay, speed is also given. Let's say 40 meters per second. That is also given. So let's visualize this. So see, there is a lake over here. There is a pump over here. It is taking in that water. That water is being taken in, and it is being taken on the top like this. It is taken on the top like this, and this water comes out at a given speed of 40 meters per second. The water which is being sucked inside, the water which goes inside this particular tube, this water flow rate, the mass which goes inside it per unit time is given to be 10 kgs per second. That is also given. The height is also given to you. The height is also given to you. How much is the height? 20 meters. So 20 meters is this basically height. So question is, what is the power if the efficiency is 50%? Meaning, if you give 100 joules of electrical energy, only 50 joules will be used to do actual useful work. First, let's find how much useful work it is doing. Then let's talk about electrical work. Okay. Is that right? Let's do that. Thank you for loving all the classes. Means a lot. So, the work done by that pump is going in two different ways. One, I am taking that water, putting it up, so potential energy. Second, I am giving it speed, so kinetic energy. So it is having kinetic plus potential. So the kinetic energy being half mv square, potential energy being mgh. But this is the work done by the pump. But what about in 1 second? That will become the power of the pump. The power of the pump will be the work done by the pump per unit time. Per unit time. So it will become half mv square divided by t plus mgh divided by t. So if you want, you can write it down as m by t common, and you will have v square by 2 plus gh. That is the power supplied by the pump. Power supplied by the pump. We can substitute and we can find out what this value comes out to be. It's not that difficult. So power by that particular pump will be, this m by t is actually mass flowing per unit time, kg per second, which is already given to be 10. So m by t is basically 10. This is kgs per second. I hope you realize this. This speed is right over here 40. So 40 square by 2. So 40 square divided by 2 plus g is acceleration, h is that height which is 20. So plus 10 multiplied by 20. How much will this be? 10 into 40 square is 1600 divided by 2 plus this is nothing but 200. This will just make it 800. So 800 plus 200, guys, that is going to be nothing but 1000. So this is going to be 100 kilojoules per second, which is the same as 100 kilowatt. That is the power of the pump. But that is not the electrical power, mind it. Remember, for 50% efficiency, whatever you are getting over here is just 50%. Whatever you are getting is basically 50%. Momentum is not a force. Momentum is a different thing. It's like, is pressure force? No, pressure is not a force. Pressure is caused due to the force. Momentum is not a force. Change in the momentum is caused by a force. There are two different things. Okay, coming over here, 50% efficiency means the electrical power. Electrical power, if you multiply it by half, then you get the power of the pump, which just means the electrical power is 2 times the power of the pump. 50% means half. So 2 into 100 kilowatt, guys, which is 200 kilowatt electrical power is being supplied. That is the answer. Is this understood how to solve these kind of questions? Everybody clear? Shall we go ahead? Everybody clear about this? No, Pavan, I don't know Malayalam. Yeah. Hello, Anugan. Oh, I believe, Pavan, you were talking in Malayalam. That's what I was wondering. Ante clasun kidilam anutho. I guess you are asking till what time is the class? Hello, Anna Suganu. I guess it is welcome or just greeting. I think you can understand many South Indian languages once you know few South Indian languages. Like I know Kannada, I can understand little bit of Telugu and Tamil. So I think Malayalam also maybe little bit here and there. I get the sense, maybe not exact meaning. Cool guys. So that was this particular problem. I hope you again enjoyed this question as well. Then there is one more thing which I would like to give you a brief mention about, and that is called as equilibrium concept. This concept, although it is in this particular chapter, is more useful later on when you study electrostatics and magnetism, called as equilibrium. See, I'll tell you what. Just some time back, I told you, whenever there is a conservative force, I can relate it to the potential energy by this formula, minus du by dx. Is that right? That is the correlation between the force and the potential energy. Imagine there is a body where the conservative force just happens to be 0 at some place. That means negative du by dx is basically 0. That means du by dx is basically 0. So a place where the force becomes 0, the derivative of u with respect to x becomes 0. Such a place is called as a place of equilibrium. Such a place is called as a place of equilibrium because the force happens to be 0. The conservative force just happened to be 0. Imagine a place where gravity becomes 0. Where will that happen? I think at the center of the earth. If you go at the center of the earth, the gravitational force will vanish. So that is a place where du by dx will be 0. Where will the spring force be 0? When you bring the spring at its relaxed condition, that's where the spring force will be 0. So there is a place always in potential energy systems where you find a sort of equilibrium. That means it stays as it is, it does not get disturbed. That is called as the place or the position of equilibrium where the conservative force is 0. Graphically speaking, what happens is, if you talk about it graphically, if you draw a graph of potential energy versus different locations, maybe that graph could have been like this, somewhere like that. You can see there are places in this graph where du by dx is 0, because if you draw a tangent, the tangent gives you du by dx. This is nothing but the slope. This is nothing but the slope of potential energy versus x graph. The slope of the tangent drawn to the potential energy versus x graph. There are places where du by dx is 0, and one of the places over here, one of the places right over here. You can see the slopes or the tangents drawn are parallel. So du by dx is basically 0. Is that right, everyone? Can you see that? Yep. NEET people also can see it, but Shreya, we already have a NEET separate session on the NEET English channel, more concentrated towards the NEET specific problems. Perfect. These are the places of equilibrium. But on that same graph, say for example, if you draw probably a tangent over here, or maybe over here, or maybe over here, or maybe just over here, the slopes are not 0. In fact, at all these places where I have marked red, du by dx is going to be a positive number. All these points marked in green, du by dx, the slope is going to be negative number. But remember, the force is negative of du by dx. So if you put a negative sign over there, so minus du by dx will be positive. That means the force will be positive at this place. Same thing over here, negative du by dx will be negative. That means the force will be negative at this place. So at all these other locations, the forces do exist and they are non-zero quantities. They are non-zero quantities. Okay. So what is the significance of this graph? The significance of this graph is it tells me which are those places where force is zero, which are those places where forces are not zero, which means how much it is, where is it positive, is it negative, positive means this way, negative means the other way. It's just telling the direction. The sign is only telling us the direction. So it tells me the force, the direction, and if at all it is in equilibrium. So that is the significance of this formula and this energy graph versus displacement. I hope till this point it is clear. I hope till this point it is clear. Right? Everyone? All right, all right. Now, out of these 2 points, although both are of equilibrium, the problem is one is a good equilibrium, one is not that great equilibrium. I'll tell you why. See, if I lift this book and if I take it more higher, the potential energy increases, this book will be unhappy. Think about the emotion of this book. The book is like, I want to go down, gravity is pulling me, why are you holding me? And I can see what it needs, what it desires. It wants to go down because if I leave the hand, it immediately drops. If I take it more up, it is starting to cry. So anything, like even a spring, if I pull it, it gets angry, it's like sad. More potential energy, it makes it sad. So you can see that over here, if I go slightly on this side, okay, wait, I'll just draw it on the next slide maybe. In this particular part, if I go slightly, if I go slightly over here, you can see the potential energy is decreasing. If the potential energy is decreasing on this side, that means it is actually becoming happier. That means it is actually becoming what? It is becoming happier. If I go slightly this side, potential energy is again falling down. That means it is actually becoming happier. I know potential energy is quite large over here. So 100% at this point, it is actually going to be a little bit sad. Compare this with this particular graph. Compare this with this particular graph. Okay, this is your x-axis. In this particular scenario, if you see this particular point and you move slightly left or right, you will see this was actually the lowest energy point. So actually it will be the happiest here, versus when you go here, potential energy increases, it becomes sad at these two places. The moment energy increases, they become sad, which tells you what kind of equilibrium this is. In this and this, both are equilibrium, but here it is very happy. Why? Because if you move it slightly here or there, it becomes sad, it will try to come back. It will try to come back. The moment it becomes sad, it will try to return. But over here, the moment it goes here, it says, oh, I can become happy. So why am I staying here? It will go even far away. Even if you move it here, it will become more happy and it will go away. So that means it will, if given a chance, it will definitely try to fall this side or that side. So it is not a great equilibrium. Hence, this is an unstable equilibrium. Unstable equilibrium. Whereas this one over here is a stable equilibrium. So in a potential energy graph, stable equilibrium is a point of minima in that graph, and unstable equilibrium is basically a point of maxima in that graph, the maxima value. So 100% then, this is minima, so this is lowest energy, so this is stable. Here when you go on the top, although it might stay there, but it is a point of unstable equilibrium. I hope this is clear. All right, tester, if a 10th grade student who has studied NCERT 11th in 9th, class 12th thoroughly in his or her foundation strong for JEE preparation. If you have studied only 11th in 9th and class 12th in 10th, okay. So NCERT if you have studied, then your foundation basics are good enough, my dear student. So after this, I would say improve your conceptual understanding to an advanced level, go deeper, go beyond NCERT. NCERT is okayish for mains, but you need to go beyond that. So test your application of concepts in multiple level of problems. So I feel you should go in-depth theory in the next couple of days and then solve more and more problems in the last year of your 12th standard. So focus on problem solving in 12th, in 11th focus on your conceptual deeper understanding, derivations and all of that. Is that clear? Yeah. JEE coaching, it's up to you. I don't know how you have studied NCERT right now. So at least join some test series. So if you think you are confident enough to crack it using YouTube, don't let it become overconfidence, because you need to actually tackle the actual competition. So at least join the test series, at least buy the PYQ books of mains as well as advanced. So you can actually solve the real life questions of previous years. Okay, cool. I hope this is absolutely clear. So we have seen what is unstable and stable. Now there is a point where the potential energy does not change only. Then it is said to be neutral. It is neither going up nor going down. Here at least if I go this side or this side, I become happy. I go this side or this side, I become unhappy. Here, whether I stay here, the same level of happiness or sadness remains. So my energy is not changing. So it is neither stable nor unstable. Such an equilibrium is called neutral equilibrium. You might be wondering, where do I encounter these kind of equilibriums in real life? You do. Just take this example. Imagine you keep a big bottle on the table. You push it slightly. I'm pretty sure you would have seen it comes back. It wobbles, but it comes back. So it is a stable equilibrium. But you take a marker pen and put it upside down. Very carefully you would have placed it. You move it slightly, it falls down. So it was in equilibrium, but it is unstable. And then you take a big box. You take a big box and place it on a flat table. Now, even if you push it here or there, nothing happens. Neither does it topple, nor does it wobble, nor does it try to come back anywhere. It just stays as it is. So such an equilibrium is then said to be a neutral equilibrium situation. Got it, everyone? Thank you so much, Pujari Harita. Means a lot. Thank you for all the love. Thank you. Thank you. All right. Is this absolutely clear? The difference between the different types of equilibrium, my dear warriors? Yep. So that was about it. You see more about this equilibrium later on when you go to 12th standard and even in SHM you will see it a little bit. Okay, so we'll see that concept as when applied in the different chapters, and if you have been attending the electrostatic and magnetism classes, then you would have seen it over there. Okay, so that was your work power energy chapter. We have completed main concepts and the basic questions right now. We'll be solving previous year questions in a separate session, and then we'll be having separate problem solving sessions once the syllabus is done. So we'll try to push ourselves till October, guys. As much syllabus will be done, we'll do it. Okay, so I want your complete attendance and complete sincerity on the channel over here every day. Thank you so much. Leave a comment that work power energy is done. Okay, I want to see that comment. Everyone put it up, and any other question, please ask it. Feel free to ask anything. Do your diligent duty, subscribe to the channel, and also like this video, mark the attendance in case you have forgotten to do so. Okay, bye bye. Take care. Have a great night. Hasta la vista.